Oh. One. Okay. So good morning, everyone. So welcome to the second invited talk at ICFP. So the talk is going to be given by Christos, and Christos Dimoulas is an associate professor of computer science now at Northwestern University, and he completed his PhD at Northeastern University with some guy named Matthias Felleisen, I think. Yeah. So he completed his PhD and he worked there on the foundations of contract systems. So after the PhD, he joined Stephen Chong's group for a postdoc at Harvard, where he dove into security-related issues, designing, implementing security contracts. And since then, he's moved to Northwestern, and he keeps thinking about the theory and design of contracts and gradual types, and spends increasingly time on trying to understand programming language pragmatics. And that's also the topic of his talk. It's called The Rational Programmer, and Christos will tell you all about it.
Hello, everyone. So I would like to start the talk with an incontroversial, I believe, statement. So one goal of PL research should be to help us understand, analyze, and improve PL design. I hope we all agree about that, okay? So over the last 60, 70, 80 years, the PL field has developed two broad ways to understand design. One is theoretical, the other is from the practice side. And I mean these two labels in a very, very broad way. So on the theory side, I have pretty much everything that uses formalisms. On the practical side, I have everything that involves realizing languages as artifacts and understanding how they are used, including implementation, corpus studies, human factors, and so on. Okay? Here comes the controversial statement. I believe that supporting PL design is a very hefty task. And just relying on these two pillars is not enough. We need something else, okay? And what I'm going to try to argue today is that we actually need something else and what I believe this something else is, okay? So to do so, I will start by telling you a little story about a little language called TypeScript, okay? So TypeScript, as we all know, is extremely popular. It's actually the language that rises in popularity the most for a number of years. And another possibly controversial claim is that TypeScript is the crown achievement of PL research of the recent years. And why do I claim that? Because TypeScript aims to use our precious types, okay, to make sense of the wild world of JavaScript, okay? So I'm going to give you a very, very simple example to show what I mean. Here we have a little JavaScript module. We have a function called logItem. It consumes an argument x, and then tries to print it after trying to turn the x into a number that has 2 decimals, okay? Of course, as you see, what we are passing actually to logItem is a string, which means we are going to get a runtime error because strings do not have the toFixed method, okay? So if we try to write the same program in TypeScript, we can use types to express our intention that this logItem function is going to use. It's going to consume both numbers and strings, okay? And even though this is a toy example, what is interesting about that, and actually the TypeScript compiler is going to give us a compile time error. But what is interesting here is that this is a true union type, okay? And for decades, we have been told that programmers do not want to use things like union types, okay? But now they keep using them again and again. And actually, if you look at what types means in the JS plus types part of TypeScript, you will see that pretty much is a collection of ideas that go back to 50 years of research in PL. All the interesting features, of the TypeScript type system, we can trace them back to things that the PL research community has been studying for half a century, okay? And their combination is extremely challenging. So, for instance, these are two of my favorite papers from the late 80s, early 90s that are trying to make sense of languages that have some subsets of those features, okay? And 30 years later, this is a paper from last year, Spopel, that tries to actually push the frontier further about how we understand the principles of languages that come with such rich features as the ones that you find in languages like TypeScript, okay? So basically, what I've told you so far is that JavaScript is a triumph of PL research, powered by PL theory, okay? But is it really? Because PL theory tells us that a meaningful type system is one that's a sound prediction mechanism. You know, the most famous theorem, type soundness. TypeScript is not type sound, okay? And we can even use this, yes, it's not type sound, and we can even use this very small example that I have here to show why it's not type sound, okay? Let's just change a little bit the type ascription on the parameter. Let's make it be a number. This should make it harder, if we were in a sane language, to call this function. We shouldn't be able to pass a string to that function. But if we run this program, the type checker of TypeScript does not complain. And what we end up getting is actually a runtime error, okay? And why is that? It's because of the any guy there that basically washes away anything about the 42 being a string and allows us to use the 42 anywhere we want, okay? Including as a number. Okay, so this is not, I want to emphasize, this is not a theoretical issue. Any is everywhere, okay? All the built-in libraries of TypeScript use any pervasively, okay? And it's not just any. There are so many other issues of unsoundness inside TypeScript, okay? Any is just the tip of the iceberg. In fact, the one that hurts more for me, the one where things get worse, is that TypeScript promises to give a seamless interaction between TypeScript and JavaScript, is untyped sister language, okay? But it doesn't really, okay? So this is the same example that we've seen before. I have refactored it a little bit differently. So what we have at the top is the definition of log item as in a TypeScript module, okay? And what we have at the bottom is the use of log item in a JavaScript module, okay? And if we run that, just like before, when we used any to wash away that 42 is a string, we'll see that when we have interaction between TypeScript and JavaScript, types mean nothing, okay? So yes, TypeScript is JavaScript plus types, but the flip side of that is that TypeScript is also JavaScript by the delete key, okay? And again, this is not a theoretical issue. This is an issue that has practical significance. This is the GitHub page of Definitely Typed, a massive repository of type interfaces for JavaScript libraries so that we can use them as if they were typed inside TypeScript code. Okay, you can see that they have, what, 35 million, is it 35? Yeah, 34.4 million users, right? And they say themselves that this is a repository for high-quality TypeScript type definitions. But corpus study after corpus study over the last few years has shown us that many of those are wrong, okay? And the reason they're wrong is because there's nothing that checks what's going on with them, right? The interaction between JavaScript and TypeScript is unsound. Okay, so the problem is not just theoretical. Again, it's a practical issue. And in fact, when human factor studies also tell us that at some level at least, developers recognize that, okay? And they say that they would prefer a sound word. So even though there are all these problems, why is TypeScript so popular? Okay, here is an explanation. It helps programmers in certain contexts. It helps them when they're trying to use their IDE for auto-completion. It helps them when they're trying to debug. So even though TypeScript is unsound, even though types in TypeScript interfaces are wrong many, many times, in certain contexts, TypeScript's type system produces actionable information that can help developers make decisions. Okay? So what is this information? That's what we should be asking. And how does it translate to actions? In order to understand TypeScript, this is the question we need to answer. And this is exactly the moral of the story. This pillar that is now shaded is exactly the thing that we're missing in order to understand TypeScript and why it's so successful, and PL design in general, okay? And this pillar is something that I call PL pragmatics. So pragmatics is a little bit of an overloaded term, so I will try to define it. It's a term that is gleaned from the study of natural language, from linguistics. It's a discipline that started about 100 years ago. It sprang out of the study of semiotics. Okay? Charles Morris is one of the pioneers. He's actually a graduate of Northwestern, my university, in 1906, I believe. Okay? Since then, pragmatics is part of the canon of linguistics. This is a textbook that is taught in undergrad classes about linguistics. And of course, the ultimate success, pragmatics has a Wikipedia page, okay? That very nicely summarizes what it is about. It is basically the change in meaning that happens to utterances of natural languages occurrences in particular contexts, okay? And just like the linguistics field has developed systematic ways to analyze and understand semantics, what I think we should be doing is also discover and develop systematic ways to understand and analyze PL pragmatics. So I'm not the first to suggest that. The first person who actually talked about PL pragmatics is Charles Morris's student, Jim Morris, okay? In one of the most beautiful seminal PhD theses ever written, okay? So Jim Morris actually said that what matters when we study pragmatics, when we study programming languages, is pragmatics. He was saying that to contrast with the predominant wave of denotational semantics back in the day, okay? But Jim Morris ended up defining pragmatics as the observations that any observer can make when they look at the execution of a program, okay? And from there, he ended up defining some very early versions of operational semantics, and of course, contextual equivalence. So instead of talking about pragmatics, he ended up talking about semantics. So here is how I understand pragmatics, okay? So semantics is all about the intrinsic meaning of a language feature, and I use this the term language feature in a very, very broad way. Okay? It's basically the meaning of the language feature in any context. And we can describe this formally with theorems like type soundness, determinism, no undefined behavior, and so on. Pragmatics is what happens to this meaning, okay, when we are trying to use this feature in a specific context, and whether trying to use the feature in a specific context results in extra actionable information. Okay, let's make it concrete. The type system of TypeScript, the intrinsic meaning, 0, okay, because type soundness does not hold, okay? But when we try to use TypeScript types to decide what method we should call, okay, when we are trying to decide how we are going to refactor the code, there is some extra information there that helps us make decision. And this positive delta is exactly what pragmatics is about. Of course, pragmatics may also result in a loss of information. For instance, if we are talking about JS, it has this very nice semantic property that a lot of its primitives never give us an error, okay? But of course, if we look at how this affects the process of debugging, we are losing information. So pragmatics in this case has a negative delta of information, okay? So studying pragmatics actually means developing tools that help us understand these positive and negative deltas, okay? I think at this point, many of you may be wondering about the following. Why don't we just ask programmers to tell us about the actionable information? Why don't we do human factor studies? Okay? So the reason that I say we need something else besides human factor studies is because if we do that, we'll be basically asking together 4 different questions. Does the PL produce relevant information? Is this information actionable and how? Are the programmers able to understand that information? And do they tend to use it as intended? Okay? The last 2 are squarely outside the scope of pragmatics. It is exactly what we should use human factor studies for. The first 2, though, I claim that they are all about pragmatics. Okay? And just like we don't need to ask humans when we are studying the theory of programming languages and type soundness, I think we can study actionable information without humans too. Okay? So in the rest of the talk, I'm going to tell you about one way that I have been working on for the last 6-7 years to study pragmatics, my instrument for studying pragmatics. Okay? It is an empirical method centered around large-scale automated experiments. By the way, I want to say, and I want to emphasize, this is just one way. I would consider it the utmost success of today's talk if some of you get intrigued and go out there and come up with your own ways to study pragmatics, because studying pragmatics is what I think is the most important thing about this talk, not so much my method. Okay, so let's go to the method. My method is called the rational programmer, and it's actually a recipe for constructing large-scale experiments, okay? So the first thing that we have to do to kickstart the method is basically pick a feature in the context, okay? For example, mixed types, like the ones that we've seen before in the examples in TypeScript, and tracking down bugs, okay? A particular context. In fact, this is an actual experiment that we have run and published about, and it's going to be the running example that I'm going to use through the rest of the talk to make everything concrete. So after we pick a feature in the context, the next step is to basically formulate a hypothesis, how the given feature produces actionable information in the given context, okay? There is something, though, that needs care here. The rational programmer asks that the hypothesis should specify a specific, well-defined strategy for using the feature in the particular context. Once we have the hypothesis, we turn the strategy into an algorithmic procedure. And this algorithmic procedure is what I call a rational programmer and gives the name to the method itself, okay? After we create our rational programmer, we create a population of scenario relevant to the context that we have. We feed them to the rational programmer, we obtain our data, and then we analyze it to refute or validate our starting hypothesis. Okay? I'm going to show you exactly how to instantiate this recipe with the running example of mixed types and tracking down bugs. But before I go there, I want to talk a little bit about why we call this method the rational programmer. Okay? So the idea behind the rational part is basically inspired by a long-standing tradition of understanding decision-making using rational agents, okay? And in particular, the version that the rational programmer is based on the work of Herbert Simon and his idea of bounded rationality, because rational programmers are agents that are not omnipotent. They can do anything, everything. They don't look for global optima. Instead, they're trying just to complete the job as well as they can. Okay? The programmer part is not supposed to indicate a real programmer in any sense. Okay? The rational programmer, I want to emphasize that, is not a model in any sense of human behavior. Okay? In fact, just putting the word rational next to programmer is an oxymoron. Okay? What the rational programmer is a device that stands in for the programmer in order to allow us to understand the systematic connections between PL design and the information that it produces in particular contexts. Okay? Cool. Okay, so let's go back to the running example about mixed types and tracking down bugs. We're going to instantiate the recipe. The difficult part is formulating the hypothesis. In order to do that, we are going to start with some research question that relates mixed types and how they affect tracking down bugs. And we are going to start with the most vague and simple formulation of this question, and we are going to iterate to make it more and more precise. Okay? The first problem with this question as it's phrased here is that it's unclear what we mean by mixed types. Okay? So the first thing that we have to do to make it precise is to specify what part of a mixed type system do we have in mind. Okay? And in particular, in this case, I'm going to focus on the enforcement mechanisms. What happens when typed and untyped code interacts, and how the language enforces or not the types at the boundary between typed and untyped pieces. Okay. So you will allow me to open the first parenthesis of the day, okay, just to explain the spectrum of enforcement mechanisms. Okay, I have a little Racket program here. This is the schematic of the program. It consists of 3 modules. We have the client, who is using a library, JSON unpack, that it's using basically to get some JSON data that it has and marshal it in some specific data structure. And then the client also uses another helper module where it passes the unpacked JSON to be summarized. Okay? It's very easy to turn this program from a Racket program into a typed Racket program, bring it from the untyped world to the mixed typed world. There are many, many ways we can do that. I've picked one. The first thing is that basically we now have an interface between the client and the JSON unpack library. Okay? This interface basically specifies the type for the exports of the JSON unpack library. Okay? It's exactly like what happens with definitely typed in the TypeScript world. Okay. I don't expect you to read all the Racket code with more parentheses. Okay? What I want to point out here is that now JSON unpack has a type that says it's a function that consumes a JSON expression plus a string, and it gives us back a list of hash tables that map strings to anything. Okay? This enables basically the client to see the library as if it was typed, even though it was never typed. The second change that I've done to bring the program that we had before to the mixed typed world is that I have typed client summarize, the helper module. And I've done that actually for real this time. I went in there and I added a type definition, and I also added a type annotation for the single function that the module defines. Okay? So what's going to happen now is, because we moved from the world of Racket to the world of typed Racket, the type checker of typed Racket is going to kick in. And at compile time, it is going to basically check all the blue code and tells us if the blue code is consistent with itself. Okay? In this case, it is consistent. But I have a bug. Okay? If you look at the code, the red parts, you will see that this function promises to return a list of hash tables, but instead, it returns a list of association lists, okay? A different data structure. My type checker cannot catch that, because this is an inconsistency between untyped code and the interface, okay? And exactly what is going to happen next depend on the enforcement mechanism that we have, okay? And there are options here. I'm going to show you two. There are many more, but I'm going to show you just two today. The first one is what I call the tedious academic, okay? It's the natural semantics that prioritize soundness. What happens in this case is that when we have values that go from the typed word to the untyped and back, those values are wrapped in proxies that enforce the expected types, okay? Which means that basically the function JSON unpack, because it goes through the interface, when it flows inside the client is not going to see JSON unpack itself. It's going to see a proxied version of JSON unpack. And when this JSON unpack returns something that does not match the type, we are going to get an error, okay? At runtime, but still an error that points exactly to the problem with the interface, okay? And not only that, the error is going to give us a little bit more information. It's something that we call blame. That's going to track, it's going to point the mistake back to the disagreement between the interface and the implementation of JSON unpack, okay? Of course, you can imagine that all these wrappers and all these layers of indirection and all this checking that is happening affects performance. And this is the reason that the second approach that I call the approach of the practitioner, which is what TypeScript implements, goes with what we call the erasure semantics, okay? JavaScript by delete, okay? And exactly this is what happened with TypeTracket. TypeTracket by default offers natural semantics, but you can also opt out and have something like erasure semantics. In which case, our blue code, the helper module, when it compiles, it's not going to have anything related to types anymore. And what we are going to be running basically is the racket program. So the faulty value is going to flow here. We're going to treat it like a hash, and hashRef is going to complain. And if we are lucky, we are going to get a stack trace. That gives us some information about what's going on here. OK? OK, cool. So we have one syntax, one type system, and two different semantics, each with its own error reporting mechanism. So I want to point out also that I'm using TypeTracket, even though we started talking about TypeScript, because the type system of TypeTracket is similar to that of TypeScript. OK, I'm closing now my parenthesis. OK, everything is balanced, and we will go back to the recipe. So now that we talked about enforcement mechanisms, we can go and refine our question. And we can say, which semantics plus error reporting mechanism produce actionable information in the context of tracking not any kind of bugs, but type-level bugs, like the ones that we've seen before. OK. In order to have a hypothesis, though, that is usable for a rational programmer experiment, we need to say exactly what actionable means. We need to be able to specify a strategy, OK? And that's exactly what we're going to do now. I'm going to introduce this notion of localization scenario. This is basically a configuration of a program where some parts are typed and some parts are untyped, OK? A mixture of typed and untyped modules like the ones that we've seen before. A localization scenario is not just a mixed program. It's a program that when we run it, it's actually going to give us at runtime a type error, OK? And our goal is to use the information from that type error to add more annotations to that program so that we can push the error inside the type region, OK? So that at the end, we reduce our localization scenario into another configuration that fails statically at compile time, OK? Because presumably, static errors are easier to track down than dynamic errors, OK? So how do we do that? One way to think about what we're looking for is basically to navigate through the lattice of all configurations of this program. And we can use the error reports to do this navigation. Error reports point to some module in that program that we believe is somehow related to the problem that we see. So we can go to that module and add types. And we can keep going like this until finally we reach at the point that the dynamic error goes away and is replaced by the static error. OK? So let's see By the way, this is a projection of a series of theoretical results that I have worked on with my collaborators over the years. In fact, on Thursday, the latest result on that, which is a collaboration with Hung Yu and Robbie Findler, who is over there, will be presented at UPSLA if you are interested in this kind of theory of contracts and gradual types. Okay? So I call this a successful error trail, because basically it's like we are following a path based on the error all the way from the initial scenario to a much simpler case. Okay? And it's successful if we finally get to the point where we get this static error. Okay, let me show you how this plays out concretely with a running example. What's going to happen here is basically the faulty value is going to give an error. Blame is going to point to the interface between JSON and PAC and the library. We are going to type check, we are going to add types to the library now, and type checking is going to fail, which means we finally managed to produce a successful error trail. Of course, this is not always the case. We can also fail to reach a green state here. And this can happen, for instance, in Erasure. We can have the same program as before, the same bug. What's happening is we're running basically Racket, and then at the end, we get an error inside client summarize. The information is not particularly useful in this case. All we can deduce is that we have to go and add types to client summarize, but client summarize is already typed, so we get nowhere. Okay? So now that we have this idea of error trails, we can finally state a precise hypothesis that is suitable for experimentation with a rational programmer. Given two mechanisms, A and B, like the natural and the Erasure semantics, for most scenarios that we have in a population, we expect that A is more successful in terms of error trails than B. Okay? Now that we have the hypothesis, the next step is to go and actually create the rational programmers. But in this particular case, what I'm going to do is I'm going to first go and create the populations, because this is going to help me make my life easier when I'm trying to define the rational programmers. OK, so in order to create the populations here, we need to create a lot of localization scenarios, which means we need diverse and a great number of type errors. OK? So unfortunately, there is no corpus in the wild that is suitable to use for that. So instead, what we've done is we took advantage of the amazing work that Ben Greenman has done, who created a diverse set of benchmarks of gradually typed or mixed typed programs. Okay? And then we took advantage of another line of work on mutation and dynamic adaptation to basically turn those type correct programs into millions of programs that have inside them type level errors. Okay? In fact, we have so many of them that at the end, in order to get a representative sample, we end up with 100,000 scenarios for our experiment. This is the corpus of our population. 70K of those correspond to type level mistakes inside the code. 30K of those correspond to type mistakes inside interfaces, like the ones that we've seen, the mistakes that we've seen indefinitely typed. Now that we have the population ready, we can go back and discuss about how we can turn our hypothesis into a rational programmer. And the population plays a role here because in order to turn the hypothesis into a rational program, into an algorithm, we need to make two decisions. Where to go next, okay, which we have already discussed. This is where the error points us. But we also have to know what types to add, okay? And here is where we take advantage of the population, because the work that Ben has done basically includes all the types for all the components, all the configurations of those benchmarks. So we can just simply go and get them from the benchmarks and use them where we need them to navigate this lattice. Okay? So in fact, in our experiment, we don't have a single rational programmer. We have a rational programmer that uses the natural semantics. We have another rational programmer that uses the Erasure semantics. We have a third rational programmer that uses the natural semantics but ignores blame and uses exceptions. And this is very useful because it's a baseline to understand the value of blame, to isolate it from all other confounding factors. And we also have a fourth rational programmer, which is basically doing random moves, and this is used to debunk the null hypothesis. Okay? So now that we have all these 4 rational programmers, we can feed them with our population of scenario. And after a lot of compute power and waiting for 4 to 6 weeks, we finally get our data. Okay? So what I want to do now is give you a glimpse of that data. I'm going to use this kind of plots that I call versus plots. Basically, they show us how one rational programmer A, fares against all other rational programmers in the experiment. The y-axis is percentage of scenario. The x-axis is basically the different rational programmers, where you see a green bar. The height of the green bar means that rational programmer A succeeds for this percentage of scenarios, whether the corresponding other rational programmer fails. Where you see a red bar, it's the inverse. The other rational programmer succeeds, where the rational programmer A fails. Of course, 2 things to observe. The first one is that the first position for rational programmer A versus rational programmer A is 0, because basically it's tied with itself. Okay? And of course, the bars, the red and the green bars, do not add up to 100%, because there are scenarios where both of them succeed or both of them fail. Okay? So let's move to the actual data. And here I have 2 versus scenarios of the natural rational programmer against everybody else. And I have 2 plots because I have divided the code bugs versus the interface bugs, the 70K scenarios in our population that correspond to code bugs versus the 30K that correspond to interface bugs. There are a few things to observe here. The first one is that the random rational programmer beats the natural rational programmer. This is not a surprise, okay? Because the random is going to try everything until it exhausts the whole program. At the end, the whole program is going to be well typed. The program has a mistake, so the whole program is typed. We know that it's ill-typed. At the end, we're going to get a static error, okay? The other thing, but there is something that basically tells us that the natural rational program does better than the random. We have also measured the number of steps, the number of modules that the natural programmer needs to add types to, and the distribution of those is much more skewed towards the small numbers than that for the random, which is more like a normal distribution. Okay, so another thing that is worth pointing out here is that for code bugs, the natural programmer beats both erasure and natural exceptions, but it's as difficult to beat erasure as is to beat natural exceptions, okay? When we go to the interface bugs, it becomes much easier to beat erasure, to beat natural exceptions than to beat erasure, okay? So basically, what we are seeing here is that blame matters a lot for the effectiveness of the natural programmer, okay? The other thing I want to point out is the scale of those 2 plots. One is just 12 there. The maximum is just 12. So if we are looking at code bugs, actually what the natural programmer offers us, the natural semantics offers us over erasure semantics is not that much. Where the natural semantics makes a lot of difference is when we consider interface bugs. Okay, there's one more piece of data that I want to say, that if we look at all the RPs and the detection rates, how many bugs they actually find, not whether we can get those bugs and turn them into static type-checking errors, then all RPs have comparable performance, okay? That means that we can use erasure semantics, we can use natural semantics, and if we care about just finding bugs, not tracking down the location of those bugs, then it doesn't matter which one we use. Okay, so to put everything together, natural semantics with blame is the best, but not by much, and not in every case, okay? Natural checks without blame, not much better than erasure, at least when it comes to actually tracking down bugs. And erasure in practice seems to be good enough. We have an edge with natural if we're trying to track down these type interface bugs, but if we care about detection or we care about code bugs, then erasure is okay, okay? So we have some evidence now through this analysis of the pragmatics of these mechanisms, of these enforcement mechanisms, that TypeScript is not such a crazy idea after all, okay? And there is another thing that we learned from this experiment, that some of the work that has been happening in the theory of gradual typing is basically ignoring the value of blame, which basically creates a blind spot for that theory. Okay, so of course, this is an experiment. All experiments have threats to validity. And maybe the most important here, just to close the loop with TypeScript, is that I've used Racket and typed Racket, and Racket is not JavaScript. It does not have the same semantics, okay? The experiment cannot, the results, the conclusions of the experiment cannot be safely projected to JavaScript. Of course, this is a limitation. If we want to draw conclusions about JavaScript and TypeScript directly, we have to repeat the experiment in that setting. I want to take a step back now and talk a little bit about what we learned from the rational programmer. So the rational programmer is basically a way to state hypotheses about PL design and try them out. When those hypotheses hold, we get back strategies that we know they work, okay, about how to use a particular feature in context. And those strategies can be used to improve tools, to bootstrap the use of these features, and also they can be used to improve documentation, okay? The other thing that we can do is we can use these strategies to teach people how to use features. And also, we can try, after we teach them, to check whether actually they like these strategies and they are able to make them work, okay? I want to say a little bit more about the teaching. The strategy that I just showed you for following error trails is exactly how I've been teaching my PhD students and undergrad students how to use contracts and how to interpret blame when they work in typed Racket and Racket with contracts, okay? And I want to make a bigger point. Matthias Feleisen and I are working on revamping a PL course based on pragmatics. Basically, we will be looking at how the evolution of programming languages can be justified through the lens of pragmatics. Matthias is teaching actually the Canary version of this course right now at Northeastern, and I'll be teaching the next version at Northwestern in the winter. Okay, of course, hypotheses can be refuted by the rational programmer. And in this case, even though we cannot really prove the absence of actionable information, remember, we just look at one particular strategy. There might be others. What we can do, if this strategy basically captures some assumption about the feature and how it works, we can invalidate those assumptions, okay? And of course, we can go back to PL design and implementation, and if we think that actually this is critical, we can go and revise our design and implementation and restart the whole cycle, okay? In fact, I want to make an even further claim here that the rational programmer experiments are in a dialogue between PL design and implementation and instruction in human studies, okay? When we succeed with a hypothesis and we validate the hypothesis derived from the design with a rational programmer experiment, then what we can actually do is try it with instruction, try to teach it to people, and try to do human studies. If those fail, this is a sign that maybe we need to go back and revise our hypothesis. And maybe this will also trigger revising our PL design and implementation, okay? I have given a very rosy picture of the rational programmer. I want to tell you the ugly truth also now. There is a price for these rational programmer experiments, and it comes in terms of time and effort, okay? We have run 4 full experiments so far, and we are halfway a 5th one. Each one is a challenge. We are getting better. We are able to reuse more and more of our experimental infrastructure, but overcoming the experiment-specific challenges always takes a lot of effort and energy, okay? And actually, the reason I mention that is because I actually want to say that this is not just my work, okay? There is a group of people who have believed, a small group of people, who have believed in this work and have helped me realize these ideas and bring these experiments to fruition, okay? And I want to thank them. In particular, I want to thank my 2 PhD students, Lucas Lazarek, who graduated last year and whose dissertation involved the first 3 experiments that we did with the rational programmer, the rational programmer method, and Nathaniel Hezuk, who has received the mantle after Lucas graduated. And of course, I would like also to thank Matthias, who encouraged me to continue down this crazy path when I presented to him in his office right before I left from Boston to Chicago. And since then has become my co-conspirator for everything related to the rational programmer. And last but not least, I want to thank the people that are behind Racket, who are over there, who have dedicated their life into producing a polished and very interesting language that is both the source of inspiration for all this work. It's the object language that we study in this work, and it's also the language that we use to implement all the infrastructure and do all our data analysis for the rational programmer. If you want to learn more about the rational programmer, there's a CACM article that presents the whole vision. I think it was out this July. If you want to learn even more than that, go to my website at Northwestern. You will find an extended version of this article because we had some space limitations. And you can find also the full collection of the technical papers about all the experiments we've done. I want to leave you with a final thought, okay? If I want you to remember something from this talk, is that PL pragmatics matters, okay? And the PL community, the PL research community, has neglected them for a very long time, okay? So this talk is basically a call to action for all of us to think about pragmatics and try to figure out ways to develop them into a discipline that is as robust as the theory and practice of programming languages that we have been developing for the last 80 years. Thank you.
Questions, please.
Hi, Harry Goldstein, University of Buffalo. Can you hear? Yeah. Hi, Harry Goldstein, University of Buffalo. Thank you so much for the talk. So if I understood your sort of data, the results you presented correctly, it seemed like there was an edge to the natural semantics, just sort of maybe not as big as you would have expected.
Yes.
And I think, you know, the ultimate interpretation of that in the context of knowing that TypeScript is really powerful and popular helps to kind of explain everything together. So I guess, what is your take on how our kind of practical analyses and analyses of humans and things like that need to kind of feed back into our interpretation of rational programmer results and things like that?
So if I understand correctly, what you're asking is how we take those results and basically we can put them in front of humans to see if this actually matters for the developers when they use them, right?
Talking about in terms of interpretation of the results.
Yeah.
I think when we talk about pragmatics, it really needs to be in the context of kind of software engineering and humans.
Yeah.
And so like, how did you go about that interpretation?
So my interpretation of these results is that given the extreme amount of effort and engineering that is needed to get a sound semantics, let's say for JavaScript, for TypeScript, it may not be that worth it, okay? And given actually the performance penalty that you have to pay because of soundness at runtime, maybe what's worth it is to develop debugging mode But of course, now you have two systems that need to be maintained. So there is a different trade-off here that needs to happen. Definitely, if someone was willing to invest and basically sit down and work all the details of a sound enforcement mechanism for TypeScript and use it for debugging, I do think that that will benefit developers. But you know, there are also economical and practical trade-offs there. So I cannot exactly, you know, give a direction here without taking those into account.
That makes sense. Thank you.
Yeah.
Hi. So this quantitative experiment, right, it started from having this corpus of well-typed programs and then slightly changing them. But that is a very, like, that's just the normie type errors, right? Like, those are the typers that, oh, I passed the lazy by string instead of a string by string. Oh, this should be a hash map instead of a tree map, whatever, right? But there's, of course, a whole other world of type errors where if you had a statically typed system, you would come to this point where, oh, no, this type error means that my whole design is wrong, my assumptions were wrong, I modeled the things wrongly, and there's no way to square this, I have to go back to square one. And this seems to be completely outside of the scope of this.
Yes, up to a point. The errors that we have introduced with mutation, actually there is a whole apparatus to make sure that they're interesting errors. Yes, you are right that those errors basically replace one data structure with another kind of data structure, or basically you may call the function with their own kind of arguments and so on. But our apparatus basically shows that these errors cause ripple effects. So the interesting errors that we choose are errors that basically the value flows a lot inside the program until it actually is being detected as being faulty, okay? But yes, this is a limitation of the study. This is one of the threats of validity, whether we can actually project these results to all kinds of type errors, including the design-related ones that you just brought up. Yes, it's a limitation.
Hi, I'm Jing Yu from the Singapore University of Technology and Design. I'm quite curious about like future work in PL pragmatics, like particularly I think you mentioned like 4 points, and then probably the second half was like human factors. So I'm wondering if you were thinking about investigating things like how programming conventions and idioms affect the usage of or the understanding of programming languages.
Yeah, I think what this is actually one of my dreams, to basically be able to conduct a pragmatics experiment about PL expressiveness. And I think this goes towards these conventions, design patterns, and all these other things that you're talking about. I don't know how to do that yet.
Yeah, like it would be great to like study how design patterns sort of evolve, right? And like it's like historical linguistics.
Yes, but I don't know how to turn that into an algorithm so that I can get an automatic experiment. You know, we can do a corpus study. There are other people that are much more well equipped than I am to do this kind of corpus studies. We can do a human factor studies. I don't know anything about humans. Okay, so I don't know how they think. Okay, that's why I'm staying into this pragmatics lane that I believe does not need humans. But yes, it will be amazing if we could figure out how we can turn expressiveness into the examination of expressiveness into a pragmatics question so that we can do an experiment. Yeah.
All right. Thanks so much.
Yeah.
Hi, Michael Kilblens, UC San Diego. Thank you for the talk. My question is maybe a little bit along the same lines. I'm curious, so I've been thinking about the distinction between the definition of a term and the connotation of a term. Right, and if you think about the semantics, they don't really take into account the connotation, right? All the sort of probabilistic information that one gets from the term being used in context. And I think there's a lot of that in programs. You know, if I show you a loop that counts backwards, you immediately think to yourself, aha, there must be some reason why it counts backwards. The programmer wasn't just feeling negative today, right? And so I wonder if you've thought about maybe like an information theoretic kind of approach, where you try to look at some sort of probabilistic notion of what people might infer.
Yes. Actually, I had one of the open questions that I had there is basically formalizing, and I think that's where you're getting at, formalizing the foundations of the rational programmer. And I think that's, we will need some encoding to do that. We will need some encoding of information, okay? It will have to be probabilistic somehow because we are modeling basically these agents. I don't know how to do that yet. But yes, that's a very interesting idea.
Okay, thank you.
Yeah.
Hi. Max New, University of Michigan.
Hi, Max.
Hi. So I think this is a great idea because we have a lot of unevaluated claims that we make in the introductions of our papers, but it's difficult for me to see how we could possibly evaluate some of the claims with this approach, right? So when I think about ICFP, functional programming, what is the main thing that we like when we make a good library design, language design, is something like it aids the programmer in modeling the problem, right? So the problem I see is that not just that programmers are irrational, but that programming is not a rational process, it's a creative process, right? And the experiment that you showed, you basically had, right, all the possible designs set up front, right, what the possible types were. So I was wondering, how could you evaluate something like this type system helps me to model the problem correctly, right, where there are many possible different designs, and how could we evaluate those kind of?
I don't know. We will have to talk. Let's pick a particular library. Let's pick a particular model that the library is supposed to implement, and let's sit down together and let's discuss. I think that's why I'm giving this talk.
Okay, thank you.
Hi, I'm Richard Eisenberg from Jane Street. Thank you. Thank you so much for this keynote. I have been not so much in my sort of research, but in my sort of other work, thinking about pragmatics for a while, and I didn't have a name for what I was thinking about. So I'm excited to have that. There's sort of a step in your talk where you say, okay, we can do these tests by sort of studying human factors, but actually these things here we can do by this other approach, and then that other approach takes years of effort. How have you sort of evaluated the sort of effectiveness of the rational programmer approach, or sort of these more experimental sort of non-human based approaches to a human based approach, to sort of see if there's one that sort of leads to I don't know exactly what the better outcome would be, but there's sort of two different ways of attacking this problem, and I'm wondering if you've looked at sort of that comparison.
I haven't. My current thinking, though, is that the questions that the rational programmer targets, they're not questions that we can answer by asking humans. And the reason for that is that humans come with biases, they come with hunches, there are a lot of sentimental things that are happening, emotional things when we program, okay? And I want to separate those completely. I'm not sure how, I'm not an expert on human factors, I've never done a human factor study, so I don't know how we could do that, okay? And that's why I went down that path of the rational programmer. The other thing that you said about the effort, yes, it's costly, but it's early. Okay, we have basically 2 dissertations so far spent on that. Okay, I believe that we are making slow progress, and I believe that we will manage to reuse more and more of the infrastructure and get the benefits down the road.
Sure, thanks.
Hello, Dmitry Volkov here from Indiana University. I'm wondering, so the examples you gave here are about how sort of error messages can guide the programmer in basically going from dynamic errors to static errors. But I was wondering how this approach could be generalized to language features that aren't necessarily related to errors.
Excellent. So one of the things that we're looking at right now, the experiment that we're working on actively, is about the interplay between contracts and testing. And we're trying to see what strategies we can use when we're placing contracts in the program to balance the amount of testing, okay? And in this case, the strategies basically involve applying test reduction approaches to figure out how we can replace some tests with some contracts without affecting the quality of the test suite, which we express in terms of mutation testing, of mutation score. So what I'm saying is that there needs to be some signal about what change we can make to the code, but it doesn't need to be an error. It can be something that has to do basically with some other metric related to the behavior of the code that guides us how we can make the change.
Thank you.
Hi, thanks for the talk. I'm really glad to see pragmatics come up in a PL context. I'm wondering how, So in human factors, or I would think HCI, the sort of bounded rationality model has really started very early. There's the GOM systems from Stuart Card, and it was abandoned because they really could get no good predictions outside of Fitts law. And this is for optimizing word processing interfaces. It wasn't, there was no concern about emotional interaction. So I wonder if we should be taking some cues from the HCI community in terms of methods here, if only because they're much cheaper than however many years to do. And I think maybe particularly there, I'm thinking about some of the issues here, even within a rational model of where you draw the bound of bounded rationality. For instance, this model assumes that I don't know the code base and I'm not familiar with it, and I haven't, but this is not how anybody programs. Yes. You're familiar with it and you share, you have built a mental model, but we can't model that in a nice algorithmic way, but obviously that's affecting it significantly. So I don't mean that as a particular critique, but as an example, are these issues that complicate this sort of approach and suggest we should back off methodologically and accept much more imprecision and confounds because we can get more information about our programs, about what we're doing more quickly?
Sure. I think the difficult part of that question, of figuring that out, is how we can scale. How we can run this, 100,000 scenarios, for instance. We need to be able to.
Well, yeah, but can I just put it in front of 5 people? Will I learn more by doing that?
It is
and it'd be a lot more cheap.
It is,
right?
it is quite possible that we can ask people, get some information, and use it to basically refine some of these algorithms, right? But again, I'm not sure if we're getting the same kind of answers to the same questions by asking people and asking the rational programmer. I'm not saying that the rational programmer is the ultimate answer here, right? It's just the beginning for studying pragmatics, and we should refine these models, and this has happened before. For instance, if you see at the use of rationality in economics, okay, there is also behavioral economics now that take bring some of these factors that you're talking about, and they are using them to model things and to run simulations and try to understand how policy affects things. So you're right, there is a path. We're just at the beginning.
Sure, thank you.
Yeah.
Hi, Michael from the University of Cambridge. My question relates to the generalizability of your claims.
Yes.
So there's been some work in human factors or in the HCI community about physics of language design, so trying to find natural laws for programming language design. And the big problem that ran into is that language design we've got a tapestry of languages, and it's really hard to generalize claims because the feeling of programming in one language is very different from the feeling of programming in another. And I think, thinking about it, it makes a lot of sense because it's very hard to isolate design decisions because you have to think about the programming language as a whole. If I'm choosing between, for example, delimited continuations or effect handlers, the type system of my language will affect how that, the error messages I come up with and how the experience of programming with one or more of these features. So I'm wondering how you see your claims generalizing and whether or not you're thinking about the limits of your approach, I guess, from a generalizability standpoint.
Yeah, okay. You're absolutely right. There is an issue of generalizability here, and I don't think we can make claims across languages. And that's the point I was trying to make here with the difference between JavaScript and Racket, basically. We cannot take the results that we have now and project them into JavaScript. But what we get is basically a blueprint for doing an experiment in a different setting. Okay? By the way, this should not come as a surprise to a PL researcher, right? Because every time we're developing a theory, we're axiomatizing the world again and again, right? And our theories do not generalize the moment we change those axioms, right? Unless if we do it in a very careful way so that the basic assumptions are conserved, okay? So I see this work mostly as, the results, the object results apply directly to the setting that I talked about. They don't go beyond typed Racket and its type system and its enforcement mechanisms, okay? But it's a blueprint that we can use. If someone wants to do, I will be more than happy to see that happening, to apply the same technique, the same method to try to understand the relationship between JavaScript and TypeScript. But generalizations are very dangerous.
We're good. May Milano, Princeton University. I'm continuing in the theme of the last couple of questions. When you're designing a rational programmer to investigate a pragmatics question, part of that design is thinking about what the rational programmer will do, so to speak. That they'll make type changes to try to change a type error, or that they'll edit some code, or maybe they'll look in one file first. And this is another point where we're making some assumptions and we're introducing our own little biases in design.
Of course.
I'm wondering if that's an opportunity for us to go back to human factors.
Of course.
Do you ever intend to, or have you thought about
If I have collaborators, I would love to do that.
Okay.
Okay, I'm not an expert. I don't know anything about human factors. As I said, I would really love to go back to human factors and try some of the assumptions that we use, because they're assumptions based on our own experiences or the theory work that I've done, okay? And of course, we're extrapolating, right? I would be very interested to go back to humans, and besides my own, experimentations with my students, in class and my PhD students, and get something more systematic that I can use to refine the strategies.
Great, thank you.
Thank you for the talk. If I understand correctly, your experimental setup was like you had different hypotheses which were about kind of like you started with the assumption that we have this system of having an untyped like library and then trying to write a typed interface, and there existing bugs basically with that system, and then the hypotheses were different ways to deal with that. And I wonder is there any way you think that you can like broaden the scope of this and say, well, rather than already assuming that we have this system similar to like JavaScript and TypeScript, and we say, well, this already exists, and we're going to try and find different ways to make it easier to work with, to debug. Can you like take a step back and say, well, should we be using like a more rigorous system that wouldn't lead to these bugs in the first place?
Sure. This depends what you're trying to, the question that you are trying to examine. Yes, what you're saying is a valid question. We can try a different design that offers more guarantees and then try and test it and see what's happening. The question that I examined was about this existing system and how it works, and why. I was trying to understand why this system that, from the perspective of theory at least, has no reason to be so successful, is actually successful. But yes, there are other questions that you can ask, and some of them is to examine basically better designed systems.
Okay, thank you.
So thanks for the great talk, Christoph. Thank you for mentioning my old mentors, Jim Morris and Herb Simon. I was wondering, so you talked about one kind of question that we might resolve with pragmatics, but there are lots of others. So one came to mind, the most basic question that we all fight over, typed versus untyped. Could pragmatics give insight into that, and how?
I think we should try to unpack what you're saying. Just like I started with a very vague question and I tried to narrow it down. I think that's the process that we need to follow here in order to take what you're saying about typed versus untyped languages and the benefits and which contexts they help and how they help. And that's research. But I do see it within the scope of pragmatics, and I do think that the rational programmer could help somehow this.
Could you give an example of an unpacked question that you think we could get insight into?
So, for instance, let's say we have certain transformations, right? And we have programs in typed languages versus programs in untyped languages. If we have a collection of transformations, how can we use those transformations in one setting versus another to refactor our program without affecting the result of the program? And
maybe we can discuss this further.
It will be, yes. I'm sorry, I don't have a, what you're asking basically is a research question, right? And I have not done the research, so I cannot say something specific, right? But yes, it's a very interesting question. As it's also a very interesting question how we can go not talk about mixed type systems, but about actual type systems and the errors that they give. Okay? There are ideas out there, like delta debugging, for instance, that has been used successfully to track down the messages, the sources of type mistakes. Can we examine, based on delta debugging, the design of error messages or error reporting mechanisms of static type systems with the rational programmer? I don't know, maybe.
Thank you, Christos.
Thank you.
Finally, I'm loud here. Thank you, Christos, for this inspiring talk. I think Christos will be around for a couple of more days.
Yeah.
So if you have more to interact with him, grab him, propose new problems, and I guess he'll be more than happy to talk to you.
Of course.
Okay, thank you everyone. My name is Matias Toro. I'm going to present this this work called Robust Dynamic Embedding for Gradal Typing. This is a joint work with Cohen Jacobs, which is the first author, which couldn't be here, Nicolas Tabarot, and also Eric Tanter. So to start, I want to give some context. I want to differentiate these two notions, syntactic typing, which we are accustomed of. We are used to it. We have static typing that uses this symbol like V' here, and we also have this notion of semantic typing that uses this model symbol right here, where semantic typings mean whatever semantic property we might want to hold. For instance, we may say that the expression E is semantically typed to tau if it reduces without errors to a value of that type. And usually what we do is we say, okay, static typing is going to imply semantic typing. So static typing is a over-approximation of the behavior of the expression. So now suppose you have a dynamically typed language. In a dynamically typed language, you have this program G, where in G we define this function f, which is a function that takes two arguments. The first one is a Boolean, or a b in this case, and the second one is an h, which is we're going to use it as a function, and then the body of the function is going to ask if b is true, then we're going to apply h with 0 and this Boolean with true, and otherwise we are going to apply h with just one argument, which is 1. And then we are going to apply f to false, and of course this is a perfectly valid program, and in fact is semantically typed to this type. So given any semantically typed function from nat to nat, then we're always going to return a nat without errors, given that the function that we receive as argument is also semantically typed. So the question is, well, what happens if we try to statically type this program? This program, we cannot statically type it because H could have like either two types, either like a function from that takes a nat to nat H is either a nat to nat function, or nat give me a nat, give me a Boolean and give me a nat and I'll give you a nat function. So so this cannot be statically typed. So one option is to use dependent types, or another option is to use Gradal typing. So we can embed this dynamically typed language into a Gradal type language by inserting unknown type annotations mostly everywhere. So this is called the embedding. So we use this unknown annotation to represent any type. So in this case, the type of B is unknown, the type of H is unknown, and we also insert some unknown annotations in the boundaries between the static and dynamic parts of the code. So in this case, we insert a cast from 0 to unknown and a cast from 1 to unknown. And so how gradally typed languages work? This program is, is optimistically accepted. Everything is fine because unknown is optimistically consistent with any other type. But this optimism must be backed up with runtime checks. So this program is going to be elaborated by inserting casts. So for instance, the argument B must be a Boolean, so it's going to cast to a Boolean. And the H is in the first application of H is also cast to a function, and so on. So these yellow ascriptions means either a cast or either an ascription or evidence or whatever you want. So if we apply, checks are inserted basically at the boundaries between terms of different precisions. So if a check fails, so in a Gradal type language, then a runtime error is produced. So for instance, if we take f applied to 1, ascribed to unknown, cast to unknown, then this is going to reduce in many steps to 1, ascribed to nat, ascribed to question mark, ascribed to Boolean. And this, of course, these casts are going to be combined, and this is going to produce a runtime error. All right, so let's go back to what we start. So we have a dynamically typed program, and we know that it's semantically typed to this type. So what happens if we embed it into the Gradal into a Gradal language? And not only embed it, but also how about if we assume or assert that this program is going to have some static type. So what happens if we take this embedding and we ascribe it to its semantic type? So what happened with this program in general? So now we have this program P where we have G prime, which is just the dynamic embedding of G ascribed to its semantic type, which is give me a nat to nat function and I'll give you a nat. And then we apply it with some arbitrary H function, which can be Gradle or static or whatever. So the question is P free of runtime errors? If the program throw a runtime error, then was it because of cast in G prime? Was it because of casts on H? Intuitively, we know that G is semantically typed to this static type. So morally, it should be the H should be the culprit of a runtime error. And if not, if G prime fails, or this program fails because of a cast in G prime, then maybe we are going to start doubting about if G is actually semantically typed to this type, right? So there are some expectations that we have because we know that this G is semantically typed to that type. So the first thing we did was check all the desirable criteria for Gradle languages that is in the literature. There is a lot of properties. Of course, this is not like a mandatory list. These are desirable, so it's a criteria. So we're going to explore two of them that has to do with the dynamic embedding programs. So for the first one, the most close one is the dynamic embedding criterion by SIG here. So it says that if you have a dynamic expression and you embed it into the Gradle program, then this embedding has to be well typed and to the unknown type. And the second part, it says that if you have a dynamic expression that reduces to some value v, this happens if and only if the embedding of v also reduces to the embedding of v. So the reduction must behave the same. But it doesn't say anything about basically ascribed expressions and only reasons about closed expressions. The other property is the blame theorem that says that, well, informally that well-typed programs can be blamed. Basically, it's trying to blame always the imprecise type between if you have a cast between two types. So to do that, you have a runtime checks that carry labels now that shows indicate the location of the cast, and they also have a polarity to know who to blame. And in particular, there is a corollary that says if you have a fully static type, then blame has to blame the context, right? In this case, it would be the blame of the context. So what happened with the previous program that we had before? So we have the embedding of G ascribed to this static type. So the blame theorem would indicate, as we have a cast here from unknown to this static type, then this program cannot fail while blaming the context. But it doesn't say anything about that it cannot blame by failing because of an ascription in G or a cast in G. Because this fact can only be derived by knowing that G is semantically typed, which is something that is not part of the property. So in this paper, we introduce a new criterion that we call the robust dynamic embedding, or RDE. And to present this, we start with first the definition of what it means to be robust. So we say that a Gradle expression is robust for some type tau if its internal cast can never fail when used with any surrounded Gradle code that use it at type tau. So intuitively, if you have an expression E, we say that is robust at gamma and tau if given any context that is well typed for gamma and tau. With a hold, yes, and we embed this with this expression in this context. Then, if this program's reduced to an error, and the error blame label L, then this location, this L, must be associated with one of the runtime checks in the context and not in E, for any runtime error that you might have. So having this definition of robustness, so we say now the robust dynamic embedding means is stated as If you have a dynamic expression that is semantically typed to some type tau under some environment gamma, then the embedding of this expression into the Gradle language and then the cast or ascription to some type tau is robust at gamma and tau, meaning that if you embed it in some arbitrary Gradle context, then and it fails, then the label associated with the error must be outside of this embedding and ascription. So in particular, we have a corollary, meaning that it states that if you have a semantically typed expression, dynamic expression, and you embed it into a statically typed context C, so a full static context C, then if you embed it into the Gradle language and you ascribe it to the static type tau, then this expression, this whole program cannot reduce to an error, because it will have to be some label in C, but if C doesn't have any cast, then it should be free of errors. So that's the criterion. I hope this is the main point. I hope you understand it. So now that we established the criterion, there might be some questions. So for instance, is this criterion trivial? Is it easy to attain? Maybe every language satisfies this criterion. Is it realistic? Maybe not. Maybe it's something that is impossible to attain. Or maybe it's redundant with other properties that are other criterion in the literature. So we tried in the paper. We tried to answer these questions. So the first one is it trivial? And therefore universally satisfied by every Gradle language? And the answer is no. So we are going to give you two examples. So let's suppose that we have a Gradle language that supports some types. And so suppose that you have a dynamic program, which is this function f, which takes a union as argument. And if it's an in-left or something, then it returns the same, the same sum. Otherwise, it's going to return an in-left of unit. So this function f is semantically typed to this type. So given a sum of 1 and Boolean, then it's going to return a sum of 1 and 1, unit and unit. Sorry. And because this is exploiting like the fact that we have an in left here. So if you believe me that, then the problem is that you cannot statically type this function f to this type, to the type that we just gave, because the first branch of the case has type unit plus Boolean, which is not equal to or consistent with unit plus unit. So what happens if we embed it into a Gradle language? So we take this function f, we embed it, and we ascribe this to its semantic type, the one there, and we apply this embedding and ascription to in left of unit. Then, well, after a few reductions, we're going to have a unit cast to unit plus Boolean, cast to unknown, cast to unit. So what happened after this, it depends really on the semantics of the Gradle language. In some cases, for instance, if you have AGT semantics, you would get an error. And the error is going to be associated with label L, which is exactly the label that we have on the ascription of f prime, violating the criterion. So AGT by default violates this criterion. And there is another work that also implements sums, but that doesn't fail with this cast. It's more lazy. So if this program reduces to unit, then it's satisfying the criterion so far. We don't know if it's going to satisfy forever, but it's not violating because of this example. So this is like a counterexample that shows that if you have to pick the runtime semantics very careful to be able to satisfy this. So another example, if it's in the context of security types, where semantic typing is no longer like reduced to some value of that type, but in this case, semantic typing could mean some like richer properties, such as non-interference. And non-interference means public output, which is low, cannot depend on private inputs, meaning high. So we can say that this function that takes an argument and subtract this argument with itself is semantically typed to give me a private NUT and I give you a public NUT, because it is constant. Basically, it doesn't depend on the input, so it should be semantically typed to this type. And actually, you can prove it using logical relations. But you cannot statically type this expression, because binary operations on private expression yield private results. So, well, you cannot type it. But so once again, what happens if we embed it into a Gradle language where we only Gradleize the security parts of the types? So in this case, this could be a type check in a Gradle language. And what happens if we apply this embedding an ascription to 42? Then this is going to reduce to 0, of course, because we have 42 minus 42. But then we're going to have a pending cast that is going to try to reduce a cast from a private number to a known to a private, to a public number. And this is going to depend on the semantics. Once again, in some semantics, it will give you an error, and this error is going to be associated with the type, with the cast that we add here, violating the criterion, or some other like semantics do not fail and satisfy, for this case, the criterion. So once again, it depends on the semantic of the Gradle language. So basically, this means that maybe this is like unrealistic. Maybe this is just impossible to, it's an attainable ideal. So is it realistic or unattainable? Well, it can be proven, and we did it for a Gradle language that supports functions, that has functions, Boolean, sums, and pairs. So we start by defining our dynamic language, which is, instead of getting stuck, it throws errors. And also, it has labeled dynamic semantics to know, we put labels on every elimination place. And also, it has something special that I'm going to explain later, that it uses lazy downcast to function types, which is important. I will go back to this. And then we define the Gradle source language, which is comprised of static semantics and dynamic semantics with cast calculus. But instead of like making all the theory on this cast calculus, we instead provide alternative dynamic semantics where we elaborate Gradle languages into the dynamic language, thanks to getting errors instead of getting stuck. And we prove, of course, that these two dynamic semantics are equivalent. So everything that we did it by using the dynamic semantics. So we did this because our formal proof is based on a notion of semantic typing for the dynamic language. So how do we prove this? We start with semantic typing. This we did with using logical relations. And this means basically that the expression cannot error and is going to reduce to values of type tau. Then we make this relation binary. And we also relax it to allow failing, but on some set of pairs of labels, meaning that if the left expression fails, then the right expression should also fail. And the pair of labels should be on this permitted set of labels. And of course, we also extend this relation to talk about unknown types, because we are going to embed this into arbitrary Gradle context. So to prove this, we prove two main properties. The first one is given a well-typed Gradle context, we prove that it is related with itself under the labels found in the context. And the second main property to prove the theorems, it's this one, that given a semantically typed dynamic expression, then the embedding and ascription of this dynamic expression embedded back to the dynamic language is contextually equivalent to itself under the empty error label set, meaning that it cannot error, basically. So if you combine the two properties, we can derive the final. We can prove the criterion. So one important thing that I was going to mention is that we have to use lazy downcast on the runtime semantics. And to motivate this, suppose that we have this function f that takes a function h, and we apply h to any divergent expression. So in this case, any lambda that diverges. And then we apply the same function to unit. So of course, this function is going to be semantically typed to this type. You have to believe me. It's a very long type, but it is. So basically, because if h uses its argument, it's going to diverge. So it's going to be semantically typed to this type. Otherwise, it doesn't use its argument. So h of applied to unit is going to terminate to unit. So we can apply, we can embed this function. We could ascribe this function to its semantic type. And then we can apply it to this function that receives something. And it doesn't use the input and return just unit. And this is going to reduce after many steps to unit ascribed to the value unit ascribed to the type unit, ascribed to a noun, ascribed to a function that to unit. So if we eagerly combine casts here, then we're going to violate the criterion. So what we basically do is we treat this lazily as a value, and only reduce this cast if we are going to apply this value to some other value. So this is something important. So, and the last question is RDE redundant to some other criteria? And as we don't have more time, we leave this for you to search in the paper. There's other things. We spoke more about other properties in the literature. We explain how we mechanize this in Rock using Iris. And we give more discussion on design choices and more cases of this criterion in other contexts. So thank you for your attention.
All right, I think we have time for maybe one or two questions. Yeah, go ahead, Phil. Or, right, there you go.
Thanks, that's really interesting work. As I recall, every other criterion in the literature is basically syntactic. Mm-hmm. It's not a semantic property. And you're dealing with the semantically well-typed property. So it can't be redundant to anything else in the literature. Did I understand that correctly?
Yes, that's right.
Right, so it's a trivial answer to that one.
Yeah.
But then could you go back to your first counterexample? I didn't quite follow that.
The sum types, this one?
Yeah.
Yeah.
So the orange there means statically typed or dynamically typed?
The orange is dynamically typed. So this is a dynamic expression.
Okay, and then you said what goes wrong is you can't...
You cannot statically type it.
You can't type it, but we don't care. It's dynamically typed.
Yeah, but we
so
want
what goes wrong?
But we know that it's semantically typed to this type, like with the type that is there. But if we assume that and we ascribe it to a static type in a gradual context, then this program is going to fail, and it's going to fail because of the cast that we added. So basically, it can fail because of the cast. So it's
so
not.
Wait, why does the unit there end up with type 1 plus b?
Sorry?
In the end, we can see this problem because unit has type 1 plus b, which it doesn't, right? It's the in left to unit has type 1 plus b, but I don't see where the unit gets ascribed type 1 plus b.
No, the function is ascribed to a function that takes a 1 plus b.
Correct.
Yeah? Where does this come from?
Yeah. Why does p reduce to that?
Yeah, we can discuss this, but it's in the paper. We have the elaboration for this. But it's going to ascribe the input to 1 plus b, which is the expected input of f. And then this is going to, maybe it's in left. It's in left. Sorry, it's a typo. Sorry, it's in left of a unit. In left of unit should be, sorry,
I see, but then we try to ascribe it type 1.
Yeah, because we entered the first branch.
Offline.
Yeah, sorry. Yeah, it's a typo. Thank you.
You should move on to the next talk. Right. So, thank you. All right, our next talk is by Phil Wadler, and it's going to be looking at a classic question about null types for pointers, and how do you deal with going back and forth between types that say you are not allowed to have nulls and pointer types that allow nulls. This is revisiting some and simplifying some previous results.
Okay, my apologies. I was busy asking a question about the previous very interesting talk when I should have been setting up. Okay. Right, so just to motivate, we've got this beautiful logo for the conference here. If you actually go to the hotel that's shown on that logo, they have their own logo, which is that, which is clearly simpler. So I'm going to give a talk about simplicity. So long ago, Tony Hoare wrote this paper. I couldn't find the paper, but I could find a talk with the title, No Old References, The $1 billion Mistake. So clearly nulls can be an issue. And languages now cope with that. So like Scala, you have this type string bar null, and you have a type string, and they're different. So if you have the S of type string and you try to assign it null, it says, no, you can't do that. If you've got string or null, it says, yeah, that's fine. And then sometimes if you say S has length, S dot length, and something that could be a null, it says, no, you better not do that. On the other hand, if you say, if S is not null, then do S dot length, they'll say, yeah, that's fine. So that's kind of the thing you'd like. Kotlin has this Elvis operator, question mark colon. You can guess why it's called the Elvis operator. And so if something has type string question mark, it's nullable. So string question mark can be assigned null, but then if you want the length of something, you'd have to say B question mark dot length. So B question mark dot is something that says, if the first thing is null, then don't do this. And return null instead, and then question mark colon says, well, if it's null, give me 0. So you always get out a number as you'd expect. So let me show you two models. So, right, we've got this in practice. Here it is in Scala, here it is in Kotlin. What would this look like in theory? So you'd like to have some theory underlying what you do. And there are two different models. So in a paper in eCoop 2020, they published them all. They had 3 different function types. So hash is a non-nullable function type. That's something that's definitely not null. Question mark is a safe nullable function type. And pling is an unsafe nullable function type. So these are 3, so you might think this is function with one of 3 different operators applied to it. No, there are 3 different kinds of functions written this way, right? Arguably that symbol should go over the arrow. So it was a fairly complicated system. But I read this paper, I thought, oh, that's, I wonder if it could be done in the obvious way. And the obvious way is you just have function types and nullable types. And so I just sort of sketched this out. And I went, oh yeah, that works. So I mailed the work that I'd done to the authors of this paper, and one of them, André Lotok, said, oh, okay, and he worked it all out in what was then called Coq, and is now called Rock. And did also so let me show you this work. And right, going back to the 2 logos, this is much more on the simpler side. I'll return to that as a theme at the end. So in their paper, they had one language that had explicit bits and implicit bits. And what I'm going to do is also have one language, but it's just all explicit. So we're always explicit about whether nulls are there or not. And I'll define a separate language implicit and give it a meaning by translation into the explicit language. And for instance, in the blame calculus, we do the same thing. We have just one language, and then we define the dynamically typed language by translation into that one language. So types are very simple. Right? A type is either a definite type or a definite type followed by a question mark. What's a definite type? It's one that doesn't have a question mark at the top. So we don't need to worry about what's the meaning of a question mark, question mark. So a definite type is either going to be a base type or a function type. And then, right, so null has type D question mark. If M has type D, then M in brackets has type D question mark. And then we've got a case expression, so if L has type D question mark, and M has type A, and N in the context where X is bound to D has type A, you get this case expression. If you want to argue with me, save that for a question at the end. But if I say something you don't understand, please just raise your hand. So just nod. If this is all too simple and you're falling asleep, please nod. Somebody didn't nod at the back. Did you fall asleep? Okay, and then we've, as always, in a gradually typed language, we're going to talk about explicit casts. So if M has type A and types A and B are compatible, where I'll let you look up the standard definition, then we can cast A to B, and if something goes wrong, we will either blame P or blame P bar, depending. And of course, if we cast M from A to B, the type of that is B. And if something goes wrong, we raise blame, and since that never returns an answer, it has every possible type. Right? This says, if I return something, its type is A, and this says, I'm not returning anything. Okay, so that's it. That's the explicit language, and then you give it semantics, and you prove the standard theorems, and I've only got 25 minutes, so I'm not going to show you all that, but it's all very standard. You can look it up in the paper if you want. So then we have this implicit language that we're going to translate it. So this is a language of implicit nulls. So our only types are iota, the base type, or a function type, but everything might be null. So to explain what's going on, we translate the types, right? We have this vertical bar translation. So I translates to I question mark, and A to B translates to translate A, translate B, and then put a question mark around the whole thing. You are all falling asleep, right? This is all very simple. And then we can define the Elvis operator, right? So L question mark colon M, I'll pronounce that Elvis. Elvis M is just do a case on L. If it's null, return M. Otherwise, it's returned the lift of X, and you just return X. So we know now that it has a non-null type. And then the translation of terms is very straightforward. This is very similar to translating a dynamically typed language into a gradually typed language. X just is X. A constant is the lift of that constant. M plus N, where plus is like plus, say, some primitive operator. Just translate M, and then Elvis it with blame op. So if this returns null, then we say, no, something went wrong. And if this returns null, something went wrong, and otherwise we'll get now a dropped, not in the question mark type, result of M and N, and then we can add them together. And then we lift the result to go back into a question mark type. If it's a lambda, we just lift it. If it's an application, again, we have to use Elvis to say, well, if that's null, then blame. Otherwise, drop it down, so we now have an actual function type, and apply that to the lifting of M. And then null just goes to null. Any questions about that? It's very simple. And then we can do some embeddings. So now what I want to do, right, there are two things you might want to do, right? You might have some explicit code that you want to put inside some implicit code, or vice versa. And we'll need some other translations on types for that. So if I want to put some explicit things into implicit, no. These are my implicit types. So I'm going to, oh, right. So this is a conversion of implicit types to explicit types. And it just says it's the one that throws away all the question marks, right? This implicitly had question marks, right? This translation put a question mark on everything. This translation doesn't. So we get something that has no question marks in it. And then if I've got a term M in the, nope, this is, right. So if I've got a term M, I think this should say implicit within explicit. Sorry, wrong label. So M is my implicit term because it's red. I convert it to an explicit term. M had type A, I convert it to the corresponding explicit type, so this will have question marks everywhere. And I do this thing, right, which throws away all the question marks. So if there were ever any nulls in here, it will raise an error. And if not, it's fine. And this says, right, it might raise an error, but if it does, it's going to be, it's going to say there's something wrong with M. M definitely has type A, but erasure of A, but you can't convert your erasure of A to a down of A. When you try to convert the erasure of A to a down of A, something goes wrong because it says there was a null in there. So this will check, are there any nulls in there? Yep? No, so remember the red types, right? Here are all the red types. Yeah. No. I want to throw away all the question marks.
You need to put the question mark on the red iota.
Oh, wait, no, you're right. No, this is fine. What's wrong?
Okay, well.
Why do I need to put a question mark on the red iota?
Because then you're removing the translation.
No, so that's, right, this is an implicit type in red. When I change it to an explicit type in blue, that's when I add the question marks. But I'm not giving that explicit type. Oh, sorry. And then, yeah, to add the question mark, that's what this does. This is A with all the question marks added in everywhere. This is A without any question marks added in anywhere.
I guess the point is that it's sort of unsafe to go to the one without question marks. And that's why
Yeah, this is unsafe, right? It might complain. If it complains, it's going to return P, saying there's something wrong with M. M corresponds to this type, but not to this type. Believe me, it's all very simple and easy. I will give proof that's too simple later. Okay, and then there's another way of doing things. Now we're converting explicit types to implicit types. And now we're going to do this again by throwing away all the question marks. Right? So D question mark just goes to D. Iota goes to itself, and A to V goes to itself. So now we've got something that might have question marks in it. Again, we're throwing away all the question marks. But now we're throwing them away from an explicit type, not an implicit type. And so now M has type A, and we want to convert it to something that we can plop into the other way around. So now we have to take A, throw away all the question marks, and then do bar, which adds all the question marks in again. And now if something goes wrong, it's not in M, because M definitely has type A, but the environment, which is treating as something erasure of ceiling of A, is looking for something that's not there. So like from here, it could pass into a function in null, but this doesn't allow the null. It's what's going on here. And you could prove something like the robustness theorem from the previous thing. It'd be interesting to know if robustness holds here. I think it should. Okay, so that's it. That's the whole system. There were some other things. So I'm very grateful. How much time have I? Oh, okay. You stood up. I was worried.
Yeah, no, sorry. You're doing good.
Okay. How much time do I have left, including questions?
8 minutes total until the next talk.
Okay. So I'm really glad that JFP talks can be presented here. I was pleased to learn that. That's wonderful. But why wasn't this an ICFP paper? Well, it's because it wasn't even an ESOP paper. So we submitted it to ESOP. And reviewer number 2 said reject. Now remember what my motivation was. In eCoop, something was published that was really complicated. And my point was we can do the same thing much more simply. So, did reviewer number 2 object to that claim? The paper shows some improvement on a Abelian calculus for nullable types due to Nieto. The new calculus is cleaner and allows more orthogonality of concerns. Yay! The construction is pretty much routine, and given the 2020 publication, the delta is far too small. So I completely agree. It's a tiny delta, it's completely obvious, but something more complicated is in the literature. Right? Should we say we'll leave the complicated thing in the literature but not publish the simple thing? That's what reviewer number 2 said, and the other reviewers agreed. So we kept bumping into this problem, so we said, right, direct to video. Just send it to JFP. And what do the reviewers say? The paper is a clear, careful, and well-written reformulation of a prior result. The result is an elegant model. Their words, not mine. That said, I have reservations about whether the paper meets the standard of a JFP publication. The root of my reservation is that I find the novelty of the paper very limited. While the presented model is simpler than the prior work, So what happened is JFP did not reject it, but came back with a huge list of requested changes that basically meant writing a new paper. And the one nice thing about the journal model, as opposed to the conference model, is you get to talk to the editor. And so I wrote back to the editor and I said, look, there's this other thing published in the literature that's more complicated. We really ought to be able to publish the simple one. And the editor agreed, and then had to do some back and forth with the reviewers, but eventually it appeared in JFP, and so I get to come and talk to you. But I think there's a very important lesson here. What is going on if we can publish something that's really complicated, but we can't publish the ones that are simple? I think that there is something, we all have built into us, well, it's got to be this much non-obvious in order to be publishable. But if something else that's worse is already published, maybe there's some advantage in simplicity. So going back to our logos, I want to say maybe we should sometimes focus on simplicity. And I will stop there. Thank you. There's something important I didn't say, which I want to say, which is this is not a complaint about any of the referees, the editors at JFP, or anything like that. They all did their job. It's just that we, as a field, have this sort of view of things. So I don't want to complain about anybody individually, but I sort of do want to complain about what we do jointly as a field.
Mm-hmm. All right, go ahead with the question.
Kimio, call me out for being very naive here, but the thing to do, if I were in your shoes, is to get on the editorial board of JFP.
I did that.
And did they accept your offer?
I was the first editor of JFP.
Oh, okay. Well, the thing to do is to get back on the board and to remind them of the values of elegance, because it clearly has been, the notion of novelty has kind of like twisted a little bit. My second question is, so again, you know, forgive my naivety, but isn't this work in kind of like, I mean, in an ideal scenario, wouldn't the kind of sequel of this work be fixing all of the code which has pure code and option code, you know, nullable code sort of mixed together, and so the idea is to sort of separate. Think of it as, you know, you have water with salt added on it, and you've got to do the very hard work of separating the salt from the water. So do you see your work in that kind of a narrative arc?
So I realized I left something implicit, that I should have made explicit, which is, of course, what does the explicit language correspond to? Scala or Kotlin. What does the implicit language correspond to? Java, where you can have nulls everywhere, that's interacting with Scala or Kotlin. So a model is modules, some written in Scala and some written in Kotlin, which I'm then trying to model very simply in this language.
So you don't see any kind of work that would perhaps transpile Java and put in the correct types if need be, and then it would look more Kotlin-like?
Well, that's another way of doing things, of course, but that's not the way I wanted to look at. I just wanted to say, take the Java as the Java and execute it and run it in parallel with Kotlin, what's going to happen, and this gives you a model of that.
One way to answer the question is that the work you're doing, in some sense, could lead to like migration paths that make it easier to do.
Simple model. Then once you've got it in the naive translation into the explicitly typed language, then you could simplify in the explicitly typed language, which would give a approach to do what you wanted to do. Thank you for that great answer, Jeremy.
Hi, Phil. Nice talk. Hi. 1, 2, 3. Hi. Is it okay? Nice talk. And I want to ask a slightly technical question. That is, I saw you shown a subtyping result on 2 of the pages, right?
I didn't mention the subtyping relationship because it's well known and because I had a limited amount of time.
I mean, is the subtyping relationship like the non-null type is a subtype of the nullable type, or?
Oh, right. In the so this is not quite the usual semantic subtyping relation. If you look at the blame calculus, there are 2 different syntactically defined relations, less than colon minus and less than colon plus, and those if something satisfies less than colon minus, it means if you do a cast from the type on the left to the type on the right, and you ever get blame, it will be positive blame, not negative blame, and the plus one is the other way around.
Oh, I see.
So if it's both a positive subtype and a negative subtype, then you know that if you cast from the left to the right, you never get blame, and that's sort of the usual definition of subtype.
I see.
So that's something from the blame calculus.
Okay, thank you.
All right. Maybe that's probably a good place to stop. Let's thank our speaker again. We are right on time, so this is great. All right. Our next speaker will be talking about, again, talking about pointers. And this time we've got parts of our program that are secure, parts that are not, and they're going to be sharing pointers. That sounds dangerous, but we'll hear how that can be done in a safe way.
Hello. I can start. My name is Cesar, and today I will talk about how to securely share references between verified and unverified code in F-star. So for the ones who don't know, F-star is a proof-oriented language in which one can verify programs. So usually one writes a program using a shallow embedding, writes a specification by annotating the code using refinement types and pre and post conditions. And then the F-star type checker checks if the code satisfies the specification, the annotations, and if the answer is yes, then we have a guarantee that the code satisfies the specification. And this was used, F-star was used to verify 2 big projects and many more, but I want to talk about these 2. Evercrypt, which is a cryptographic provider that's verified in F-star, and code generated from F-star is now part of Mozilla Firefox, the Linux kernel, and the WireGuard VPN. And Everparse is a framework for secure parsers, and parsers verified using this framework are now part of Windows Hyper-V, and which is part of Azure Cloud. So these projects got integrated into larger code bases. However, mixing verified code with unverified code can be problematic. And this is because the interaction between verified code and unverified code is usually assumed, meaning that the behavior of the unverified code is assumed. So because there is no guarantee that these assumptions are satisfied, if the code, the unverified code is buggy or malicious, this can lead to unsoundness and insecurity, which will break our verification. So the solution we propose is to enforce the assumption on the unverified code by using dynamic and static enforcement. And we want to do this in such a way that we have here, we are able to write a global specification about the whole program. So we want to state a specification that relates the initial state and the final state of this whole program. So in our setting, both the verified code and unverified code are stateful programs. You can think of them as being written in the same language, but one is verified, the other is not. And they can dynamically allocate first-order ML mutable references. These are also known as full-ground references. And it means that they are typed references, they are unfreeable, and they are also unforgeable. And also in our setting, the 2 can share references dynamically between them. So in this setting, what we do is that we use dynamic enforcement to enforce the assumptions that the verified program makes about the unverified code related to the shared references. So you can imagine that the verified code can expect from the unverified code a reference that should contain a sorted list. This can be an assumption one writes. Obviously, there is no way to guarantee that the unverified code gives us that. So we enforce this using high-order contracts. And what we enforce statically is that we prove that the unverified code modifies only shared references. So the intuition behind this is that we treat the dynamically allocated references of the unverified code as being shared. And also, we know that the unverified code cannot get their hands on the references of the verified code because they are unforgeable. So these 2 ingredients are enough to get back our specification, and we had to have a proof, a mechanized proof, that our whole program satisfies the specification. And to make it clear, this proof is done for any piece of unverified code. So given a verified program, and given that's verified with related to this global specification, this can be linked with any piece of unverified code, and it will still be secure. All right, so to obtain this result, to have this strong guarantee, one has to use SecRefStar. It's a tool, a framework we introduced. It's a verified secure compilation framework for the sound verification of stateful parser programs. So one can verify a stateful program using SecRefStar. During compilation, the higher order contracts will be introduced. And then The compiled program can be linked with any piece of unverified code. And secref star is shown to be sound and secure as long as the verified code and the unverified code are shallowly embedded in F star into a monad that supports terminating higher order stateful programs. Yeah, so this part of F star is secure. We obviously have extraction to a camel, but that's not verified, so it's not part of the talk. So I would like to give you a glimpse of 3 of the contributions of the paper. First, how to verify soundly partial programs. I will give you some intuition about why secref is sound and why it is secure. We prove about secref star that it preserves observational equivalence, non-interference, and trace properties. So here we have a program, and on the right we have a model of a heap. So this is a higher order program that takes an unverified library as an argument. So the unverified library is of type ref of int and returns a callback unit to unit. And the first thing the program does is that it allocates a reference where it keeps a secret. It will appear on the heap. It allocates R, which is a ref of int. And then it calls the unverified library, and it passes R to the unverified library. So what happens in this moment is that R gets shared, and also where R points to gets shared, which brings us to the property of sharing is that it's transitive and permanent. And now, because the unverified library has access to R, we don't know how the unverified library modified R. It could stay the same, it could not, we don't know. Next, the program allocates a new reference and updates R to point to this new reference. And then it calls the callback that it got from the unverified library. So here we call the callback with unit, but this callback still has access to R and R prime. And by rereading R and R prime, it will also find this new location, which means that this new location is also shared. And now we see that looking at what references get shared is not as easy as looking what references are passed. We pass directly only one reference, and that's R. But here, 3 references got shared. And because this makes tracking what's shared tricky, and when here to be able to verify this program on the next assertions, we have to be able to answer the question, what references can this callback modify? And so this is an assumption we make about the unverified program. And if we under-approximate, we risk to be unsound. If we over-approximate too much, we risk to not be able to prove this assertion. So to tame this complexity, we propose to over-approximate what references get shared using labels. So we introduce a labeling mechanism that's encoded in F star, so we don't change anything from how F star works. And this labeling mechanism is computationally irrelevant. This labeling mechanism doesn't exist at runtime. It's used only to do proofs. So fresh references are labeled as private, start as private. And then we have a dynamic operation that the user can use to label a reference as shareable. And there are 3 rules. Once a reference is labeled as shareable, it's forever shareable. Shareable references are only allowed to point to shareable references, and only shareable references can be passed between the verified and the unverified code. So having these rules is enough to verify our code. And let's look back at our example to see how that works. So now you see that in the heap, we have a ghost map that maps references to labels. But again, this is Ghost. This doesn't exist at runtime. But during proofs, this map will get updated. So this is why it's kind of a dynamic operation. So the program allocates the secret, and it will be start as private. It allocates R, it starts as private. And then the user has to use this dynamic operation manually to label R as shareable. And the user cannot forget to do this, because part of secref, the assumption made about the unverified code get extended. Now we assume about the unverified library that it accepts and returns only shareable references. So when the user tries to call the unverified library, they actually have to prove that R is labeled as shareable. And because we are in F-star, this is done using the SMT, which simplifies things. So again, we don't know how R and R prime get modified. And the user also has to, when updates the shareable references, again, the user has to use the dynamic operation. And this is because now the update states that, okay, if you want to update the shareable references, then you have to prove that the new value also is shareable. And now when we call the callback, we can do something very nice, is that we can use the labels to strengthen the postcondition of the unverified code. We can say that the unverified code modifies only shareable references. And and this is very helpful because next, when we try to prove our assertion, we see that secret is private. We know that the calls into the unverified code modified only shareable references, so we can prove that secret stays the same. So I showed you how one verifies a program. I would like to talk more about how the program assumes what the unverified code does. So the assumptions are all in the types. And we say that the verified code assumes a strong type of the unverified library. This is a type that contains refinements and pre and post conditions. So here we see that the unverified library is a function that takes a ref of int and returns a computation in LR. LR is our shallow embedding using a monad. And this monad is special because it has a precondition. So this precondition states is a predicate over the initial heap. And it has two parts. The first one is specific to secref star. It states that R has to be shareable. And the second one is user provided, and it states that R has to contain an even number. The monad also gives us a post condition, which is a predicate over the initial heap and the final heap. And the first two are specific to secref star. Between the initial heap and the final heap, only shareable references get modified, and the return value has to be shareable. In our case, it's a callback, so that's considered shareable because it's not stored in a reference. And also we see a last conjunct that states that R has to be unchanged. This is again something specific to the user that user gives. So the user uses this strong type to verify the program, and then during compilation, this type will get simplified to something we call an intermediate type. So compilation, in our case, will convert the user-provided predicates into dynamic checks, or some of them will even be enforced statically. So here, in the precondition of the unverified code, we have this predicate that will be statically verified when verifying the code. So actually, this doesn't have to be enforced dynamically. But the second one is a post-condition of the unverified code. There is no way to know statically that the unverified code doesn't change the the value of R. So here, what we do is that we add a higher order contract that will save R before calling into the unverified code, and then do the dynamic check when unverified code gives us back on control. Yeah, this is a standard stateful contract. And finally, the intermediate type will look something like this, which now it contains only predicates specific to SecRef star, our framework. What about the unverified code? We say that the unverified code has a weak type, and we can bring this weak type to an intermediate type. So let me show you how we do this. So actually, we take advantage of polymorphism by parameterizing the type in the specific predicates of our framework. So first, we use some notation. We use phi to define is shareable, and then modifies only shareable. We denote with less than equal. And then we parameterize this type into these predicates. So now what happened is that this type doesn't have any concrete specifications, which we say that it's a correct representation or appropriate representation for unverified code. And what's nice about this representation is that if we instantiate back this type with our predicates, we get the proof that we want, the type we had earlier that states that unverified code modifies only shareable references. So we get this basically for free when doing this. So the full details of this are in the paper. Here I can say that this type is also parametric into the operation of the monad. And those operations also use this phi and less than equal, like the parameters. And they compose really nicely, and this allows us to do this claim of that it's unverified code. And also we have a translation from a deeply embedded language into this representation. So we really think that this is an appropriate representation. Okay, so we saw how to verify a partial program. I gave you some intuition about why it's sound, and I want to talk now about why it's secure. So it's we prove about our compiler that it satisfies robust relational hyperproperty preservation. This is a strong secure compilation criterion. It's the strongest of the work of Abate et al. And it's specifically stronger than full abstraction. So compilation, in our case, preserves observational equivalence. So this is what full abstraction gives us. But our criterion also gives us that it preserves non-interference, and it also preserves trace properties. And it's usually very hard to prove, but our proof is by construction. We use shallow embeddings for the source and target language, and we have a specialized design of the higher order contracts. So there is more in the paper that I do not have time to talk about. I didn't talk at all about the shallow embedding, which is the extra monad. And actually, we give a monadic representation for monotonic state, which is the main way to verify stateful programs in F-star. It was previously fully axiomatized in F-star. Now it's a lot less. And we give a proof of soundness. We show how we encode the labeling mechanism on top of this monotonic state, and we also have more labels for higher order settings. And also we have an interesting case study of a simple cooperative multi-threading scheduler. So the scheduler is verified, but it schedules unverified threads, and we still are able to prove that the scheduler is fair. Yeah, that was it. Thank you.
All right. Do we have any questions? sorry, you're there first. Go ahead, Sean.
Hello. First of all, thank you for the talk. I thoroughly enjoyed it. I recall from some of the gradual typing literature that sound gradual typing can have some quite unfortunate performance trade-offs. I know that some work has been done around static analyses to try to lessen these issues. But given that F star is in a dependently typed setting, I'm curious whether or not you have an idea for how the more complex type systems interact with these dynamic contracts with regards to performance overhead and whether or not you've done any benchmarks on that.
So we did not do any benchmarks. So we only enforce properties, predicates about shared references. So in a way, and we don't look at the unverified code at all, right? We don't apply any analysis to the unverified code. So basically, we don't have any way to know if this predicates hold or not, except doing a dynamic check. So these dynamic checks are unavoidable. Because they are only about the shared references. The other properties enforce statically, so we save a lot of time on that. And I think there is some related work that adds dynamic check also for that, like to make sure that the private references of the verified code stay the same. We don't have to do that, so that is an improvement on our side.
Okay, makes sense. Thank you very much.
For your talk. I know that in Jane Street they tried modifying OCaml compiler to add some modes to it, and in particular they added local and global mode to variables. But in their application, it's for optimizing heap allocation. But they have very similar rules. They have like, if a variable is local, it became global, then it never becomes local again. I wonder whether you looked at this work and maybe they have similar implementation, or maybe they have similar properties, or maybe your is completely different. Yeah, what's the relation?
So our work is more coarse-grained. We split into verified and unverified code. Their work is more fine-grained. It's at the level of each function, right? And also we are in the setting where we verify programs that are shallowly embedded in F star. And I read their paper, but I don't know a good way to shallowly embed the modes they are using into F star so that I can take advantage of them, so that I can verify the code and then extract, right? So if you have any ideas about how to shallowly embed modes in F star, how to shallowly embed modes, then I'll be happy to hear about it.
Okay, thanks. First, I need to understand what does it mean to shallowly embed modes.
This is kind of maybe a follow-up question about the overhead of the contracts. So I guess maybe one way to phrase it is when you're doing those higher order contracts, does that involve creating proxies on the references or no?
No.
Okay, cool. And then follow-up is, does it are those checks always sort of like O of 1, like time complexity, or could they involve like traversing a big chunk of the heap or something like that?
Right, so something I did not say is that the predicates are written, they are logical predicates, and we don't have a way to convert them to dynamic checks automatically. So the user has to provide these dynamic checks.
Okay.
And here it's the user who decides. I suppose it's a balance between having very complicated predicates that take a long time to enforce, or maybe relaxing a bit. But again, these are about shared references, so one doesn't have a choice but to dynamically check what happened there.
Okay, great, thank you. All right, let's thank our speaker again. are now, I think it's time for lunch.
Yes. Mic test, yeah.
Hi, welcome to this session. I'm Alex Kavos. We have 4 papers for you. We have one paper on indexing the length of lists in a way that makes doing circuits easy. We have 2 papers on normalization for dependent type theory, one on normalization, one on its uglier cousin, canonicity. And finally, a paper on higher order store. Let me invite Craig Roy to the stage to listen to Foals Seldom Differ. Foals of fools.
All right. Hello, my name is Craig Roy. I work on compilers and programming languages at Quantinuum, along with these 3 other people. Together, we are Team Brett. That's a functional programming language we're writing for writing quantum programs. But that's not the topic of this paper. This paper, I'm going to present an equation solver for a subset of the natural numbers that we intend to use in our language. This is has Connor at the heart of it, which will become very clear if you read the paper. The title is enough. Right, so we're going to pick a subset of the natural numbers, prove completeness of equation solving, and in order to demonstrate this, we've cooked up a small programming language called Foobarn. We did this because we're writing our programming language Brat, which you write quantum programs by metaprogramming, writing classical programs that write quantum programs. The goal is to classically make guarantees about the safety of the things that you're going to run on the device. And our abstraction is that we have vectors of qubits, and you're applying operations to those, which has got us interested in ways to talk about vectors. Our users have programs that have lots of structure, so we want to provide ways for them to express their structure in our language, ideally. Also, because we're a quantum programming language, we have linear types for qubits, which we'll go into in a minute. But this is our little language. It should be easy enough to intuit for this crowd, I hope. The main thing is that we have functions indexed by type level numbers, and we have built-in vectors which are written n of x, n of y. We have polymorphism over types as well, but there's nothing novel about that. And in the clauses, you can pattern match on the numbers. And we have fancy vector patterns. This is just cons, but it's written in a weird way. This comes from Connor's experience teaching in university, where people are always confused about, first-time students are always confused about which is the head and which is the tail when the operator is symmetric. So we have a point to note the element and then an arrow to the long part. And in our language, we can infer all of these numbers, so you don't need to write them. Right, and we're interested in equation solving for a couple of reasons. Well, we want to type check functions like this. We look at the clauses so that we can check that the patterns make sense against the number arguments that we expect, and we can create refined number variables to use on the right-hand side. For example, if we use the nil pattern, then n must be 0. If we use cons, n must be a successor, which we write as a big red S. And when we're making function calls to type check this, you have to make sure that the number that you pass in matches the type, the argument type of the function you're calling. Here we infer head m, but we need to check that m is a successor because head expects a successor n of x. And this is what a vector of n plus 1 x's looks like, Sn of x. And when evaluating, we also use this to choose which branch to run. So we're interested in equation solving, and this is not an important example. This is just something we do right now in BRAT. We have vectors of qubits, and qubits are linear. We can do a big fold over our whole list vector of qubits, and that's great, but cons can only get you so far. What if we want to look at something in the middle, do something like split at in Haskell? It's going to be a pain to guarantee that it's safe, because you pass in a runtime number and you have to guarantee that's less than the length of the list. So we want something better. So you'll recognize this from Satnam's keynote yesterday. This is Batcher's merge sort. We're not specifically geared to quantum. Anything that has a divide and conquer structure, this will be useful for. In particular, quantum programs and classical circuits or digital logic are inherently parallel, and that's the kind of angle we're going for with this solver. So the important thing about the merge sort is the structure of the algorithm is recursive. This big red box is sort n, and we have two implementations of sort n minus 1. We split our inputs in half and pass each into sort n minus 1, and then collect them all together in a big merge box. This is n equals 3, and you can see we have 2 to the 3 inputs and 2 to the 3 outputs. And we can go one level deeper. For illustration, each sort n minus 1 contains 2 sort n minus 2s. And then at the bottom, we have a bunch of these compare and swap elements, which is just something that's passed into the function for whatever type that you're calling it on. Compare and swap takes 2 arguments, compares them, and swaps them so that they come out in a sorted order, but it's always for 2 elements. And we can write this in our programming language. This is just another level deeper with all the detail. This is the version from the paper. So you can see the wires a bit more clearly. So in our language, you can take the type of sort. As I said, it takes 2 to the n inputs and has 2 to the n outputs. We're taking some compare and swap thing. But what's going on with the vector pattern in the middle? On the last line, we have sort cast t, x's equals and equals y's. We call this the even pattern or operator. And what this is doing is splitting everything in the middle. And the second part of this is the merge, which takes two vectors of size 2 to the n. And the details aren't important, but we have another operator on the third line. We're using this equals percent equals pattern, which does something slightly different, but also needs to guarantee that we have an even length vector as the inputs. And there's lots of crazy patterns going on, but that's not important. So our full list of vector patterns in the language that we've found to be useful for this. On the top, we obviously have the empty vector, cons, and snock, which have the same types, but elements swapped around. And then on the second row, these are our novel operators. The first one I call even, then riffle, then odd. The first two have the same type signature, but odd requires an odd list, or an odd length vector. So the type at the end is successor of double of n, as in anything times 2 add 1 is going to be an odd number. And this is the illustration of the semantics. For odd on the top, we have a black element in the middle, and then blue and red things, and they all slot together. The ampersand thing is just meet in the middle. And then the percent sign is less intuitive. It takes all the even elements and the odd elements and alternates them to build up the list. I think Satnam referred to this as the butterfly operation. Close enough? So this gives us a bunch of equations we want to solve if we want to be able to type check problems like these. We need to know if things are even or odd, check if they are, if our inputs are 2 to the n of something. And in picking a way to represent these equations, there's lots of arithmetic out there. So we've applied a bunch of prejudices to reduce the search space. and decided that things are easiest if we keep it to monotonically increasing functions in one variable. Obviously, the way that this is usually done in dependently typed programming languages is you have functions in any number of variables on the right-hand side. So for example, concat has output type of length x plus y. We want to avoid that because it's very complicated, and we want to keep things easy for ourselves and mechanizable. So in order to write the type checker for this, we have a bunch of helpers. Unz is asking if a number in our language is z. Our language here, as has been alluded to, we have 0, successor, and double. Successor in z has no solution, which we represent as nothing in this pseudo-Haskell, just in black and white, because I don't know how to use the syntax highlighter. I didn't write myself. But double is 0 when it's double of 0. And we can peel off successors and doubles as well. The part to keep an eye on here is the successor versus double case, because then we have to add 2 constructors instead of just 1. For example, on the bottom left, if we're taking the predecessor of a double, then we have to half it, take double, sorry. We have to half it, take the predecessor of that, and then double and add 1. And this is kind of unsatisfying because the rest give us just one thing or nothing. So we add an extra operator called bubble, which is definitionally just successor of double of something. And this makes things a bit nicer, namely the lines in blue. And we can easily write the unbubbling logic. So now if we want to add power to the language, things get interesting. At the start, it's easy. Is power 0? Never. By power, I mean 2 to the n of n. So pn is 2 to the n. Undoubling, that's easy. That's just p to the n minus 1. And unbubbling is only valid when it's 0. But writing the predecessor of power is quite tricky. So we could have something like adding power of n minus 1 for all the predecessors of n, but then we have many powers of the same variable, and we want to keep things to just lists of one function in that variable, all composed with each other. So it turns out what we want is actually to take the predecessor of double and put that in our language. So that makes things much easier to write, and this is the key observation of our paper, that full is much better behaved than power. Why is it called full? If you think in binary, 2 to the n minus 1 is all of the ones for your vector of bits, versus power, which is just 1 followed by a bunch of zeros. So we call this full, and it behaves very nicely with our other operators. Full of n is 0. If n is 0, I've cheekily added an effect to the fake Haskell here, because if we get to this case, then we can define n to be 0. We want that to bubble up to our unification environment. And it's a little bit nasty. Well, what's nice is that bubbling full gives you the next full, as in the un-s case here. But what's not nice is that we have to add 2 constructors there, which we would like things to be nice and uniform, and it's only pop out 1 constructor, but what can you do? Normalization of these things is fairly easy. We just have a couple of rewrites. We push all of the f's inwards, we pull all the s's outwards, and we have the d's in the middle. There's a nice proof of this in the paper, that we only have to prove that they align for I equals 0, 1, or 2 to have to be the valid normal form. But now the more important part is we want to prove that we have complete equation solving. That is, for every 2 numbers in our language, every equation of 2 numbers, we can put out a solution. And moreover, we can spit out the best solution. So the way that we prove this is we have a subset of a subcategory of set, I suppose, with the empty set, the unit set, and the natural numbers. And we take all of our SDBF constructors as arrows from n to n. We can always produce a z if we have upside down exclamation mark, which I should have thought of a name for. Let's call it GNAB. That means that we've failed. There's no possible solution, and that's a valid, that's an expression in our solution language that there's no possible way to unify these 2 things. So you should give up. And identity arrow, obviously. So, yep. So for example, the way that we're talking about this in terms of pullbacks in our category is if we have an equation like dn equals fm, then we model that as 2 arrows pointing into the same target, and then we draw the pullback with the arrows that would have had to be, so that it's the most general solution and not just a random unifier. So the top case, foo of something is equal to d of something only when the 2 things are the same and they're both 0, is how to read that. And the bottom thing we have is successor of n equal to 0, no. So a couple of upside down bangs as the arrows. And the observation is that the tricky thing about our equation solving is foo, because if we try to take the predecessor of foo when we come out with 2 constructors instead of just 1, as with every other case, if every equation gave us a pullback with 1 thing on the arrow in the result, then we could tile everything squarely and it would all be fine. But we have to work a little bit harder. So we observe that we can express all sequences of arrows in coin, not ZSDF. In our category of solutions, all sequences of arrows can be expressed as a bunch of these nice, well-behaved arrows, lowercase f, followed by 1 problematic f, which can be these sort of bottoming out cases. Identity where it's equal to some number, or it's impossible, or it's 0, or it's full. Okay. So if we can solve for one of these things, then everything we can express is a sequence of these things, and it all composes, and we're happy. So what we need to do to prove completeness is fill in this square, and I have less time than I thought. So the first thing is well-behaved things are well-behaved. So we just get more well-behaved things out. And then when we pit them against less well-behaved things, then we either get a double at the start or we don't. So pulling back this G star along F on the top, pulling F along G star gives us S, which can be a double or no double, followed by a badly behaved thing. And we can tile out rightwards and downwards with that because it's symmetrical. And these double or not double, they spit out things of the same length, the same amount of doubles on the head. And we have a couple more lemmas, followed at last by poorly behaved things solving for more poorly behaved things, which completes the square. And we're happy that any equation that we can express in the language can be expressed as f, small f after big F, composed with a bunch of those. And if we can fill in the square for that, we can come up with a solution for everything. This is a quick outline of how we implement this in a unification algorithm. We just call out to the unz, und, unb things that we had before. There's a couple of extra things here like numdef, which is just defining numbers in the environment. And we're spitting out delta, which is a refined context. And we have a proof for this. We have this implemented in Rock. And we made the termination checker happy with this measure of progress, which isn't the nicest thing, but it works. So things are always getting smaller, but not always in the same way. So rounding up, we tried other approaches like all of the GHC extensions that Satnam showed in his keynote, and they fell over on the more involved cases when we have nesting of multiple fools. And things like SMT solvers, they don't have the completeness property, so when we put in more complicated equations, they fall over at some point, whereas ours doesn't. In our language, we have existentials, and the solver is just as good at working out what the output should have been, what the output should be as it is what the inputs should have been. Future work is there's no reason to fix doubling and power of 2 as our base. If we could do this for every prime number, we could have more numbers in the language, and everything is proved in the. All of the proofs that I mentioned are in our artifact, and that's everything from me. Thanks.
I would like to invite anyone with questions to queue up on the microphones.
Thank you for the entertaining talk. Isn't it a bit sad that you cannot have a sum, as in kind of concatenate array, like shapes of arrays?
So we're taking a very principled isn't the word, strong-headed approach, that doing things like concatenation is throwing away structure, and if you have a pair of vectors, you can keep it as a pair of vectors, and then it's more representative of your problem.
And what if you want to map over those vectors? Then you have to keep writing helper functions that will do it for 2 and 3 and 4 vectors at the same time.
I think we can solve that problem.
Cool.
But we have other things going on to address mapping over vectors.
All right, thanks.
Thanks.
Yes. Okay, in that case, I'd like to ask one. Maybe, sorry, this is going to be an annoying logician's question. Essentially, what you're doing is you're deciding a very, very little fragment of arithmetic. Is this a known fragment? Is it something that people have identified before? Is it just something that was useful for your particular application only?
I don't think it's been done before, and it's a step up from using Pressburger arithmetic. So anywhere you want to slot in an equation solver, then you can safely put in this one.
Thank you. All right.
I can ask a second one, since you mentioned Pressburger arithmetic. In terms of the complexity, is it sort of comparable to Pressburger, so doubly exponential, or is it? Have you considered any complexity results for solving in this language?
No, we haven't considered the complexity, only completeness and termination.
Okay.
So we don't have actual performance or complexity information.
But if it's a step up, then probably it's at least doubly exponential.
Step up in terms of expressiveness, I mean.
Oh, I see. Okay, cool. Thanks.
For something that's complete and decidable.
What were normal forms? Are they just SSSSZ, or you have?
So you're putting all of the. You're not mixing constructors together. So any number of S's, which you can just represent as in binary in your programming language is n plus, and then the rest of these things. Then you have a number of doublings, and then some number of fools. So they're all getting sorted into their own little buckets, S's, then D's, then
But
S.
some of these are equal, right? So is this unique? Are these normal forms unique?
Sorry, I'm not sure what you mean.
I mean,
like two
they represent
equivalent
natural numbers.
two-
Aren't there two natural numbers which can be represented? Isn't there a natural number which can be represented by different normal forms?
So they're not natural numbers, they're like equations in natural numbers. So any two terms which are equal for all natural numbers have the same normal form.
Okay.
And vice versa.
Please join me in thanking Craig once more. What to remove? Okay, so Shangyi Jiang will now tell us how to do normalization by evaluation when universes are not so nice, by which I mean that they're not cumulative.
Hello, everyone. My name is Shangyi Jiang, and today I'm glad to introduce our work, normalization by evaluation for non-commutativity. And this is a joint work with Jason and my advisor, Bruno Oliveira. So the talk will be split into 5 parts, and first we will talk about background and motivation. This will also cover the high-level ideas of our work, and the next 3 sections we will develop our proofs more detailedly in 3 parts. And as a final part, we will give some conclusions and also final remarks. So without further ado, let's go into the background and motivation section. So people in this venue should be all familiar with dependent types, but still let me introduce it a bit. So in simple type systems, types and terms are separated. So types classify terms and terms perform computations. In dependent type theory, this separation becomes blurry. So types themselves can depend on terms. And then once again, we have this very classic example of dependent type systems, which we have a vector of a fixed length, and this length can be included in this type. But we all have another question that if this, with this blurred separation, what are the type of types? Or in our terminology, we call it set. So set, if we give set to set itself, then it leads to Girard paradox, which breaks the consistency of this type theory, and we can now use this type theory as a basic or foundation of a proof system. So that's definitely not something we want. And one solution is that we stratify types into universes. For example, in this case, we have natural numbers living in the zeros universe, and the zeros universe living in the first universe, and so on. This kind of stratification prevents self-reference and paradoxes. And with universe, we have different ways to design universe hierarchy. So suppose we have this natural numbers lives in the zeros universe, and this is the traditional cumulative rule, which says every type lives in the smaller universe also lives in the higher universe, which means T lives in the set I, also a type. T is also a type in the set 1 plus I. And you can apply this rule multiple times so that you can lift types to any arbitrary higher universes. In ROC, cumulativity is enabled by default. So if you have a type in universe I, it's by default regarded as a type at the universe J if I is smaller than J. So in Agda, things are a bit different. The non-cumulativity, which is the absence of the cumulative rule, is enabled by default. So you cannot write this function because A only lives in the set L, but not set L. So Agda, in its standard library, it provides a manual adjustment, so you can lift a type to a higher universe by this lift in the Agda stdlib. In general, these 2 kinds of universe hierarchy have their own pros. So for non-cumulativity, usually you enjoy typing uniqueness, which means any typable terms are given a unique type up to equivalence. And also it induces simpler constraint solving if you have universe polymorphism, because all you need to do is to use unification to solve the universe level. With cumulativity, people can also argue that it gives a more intuitive set theoretic explanation, and it increases the expressiveness of this type system. The cumulative rule not only differ in this, but if we think about their typing rules, this design choices also influence other typing rules. For example, in the cumulative setting, the pi formation rule for both domain and codomain types, they can reuse the existing universe level. But in the non-cumulative setting, we have more precise universe level control, which the pi type lives in the max JK universe level of its domain and codomain type. We can also abstract over actors' manual universe level manipulation rules into these three following rules, which we have a lift type constructor with also its introduction and elimination forms. But for a dependent type system to really work, we usually want some computation on types. For example, we want this f can be applied to this variable x, even though their types doesn't match exactly. So it means our type checking or the type theory must consider some equivalence relation. A reasonable equivalence relation is a definitional equality, which can be viewed as a reflexive, symmetric, and transitive closure of beta or sometimes eta equality. And we want our normalization or type checking or the conversion checking algorithm to enjoy the following two properties. The first being soundness, that says it normalizes a term to an equivalent term. And second is a completeness, that given two equivalent terms by this equivalence relation, our normalization algorithm gives the same syntactic normal form. Normalization by evaluation is a widely used technique to achieve normalization. It's a method of obtaining the normal form of terms by appealing to their denotational semantics. A term is first interpreted into a denotational model, and then a canonical, mostly beta normal and eta norm representative is extracted by reifying from this denotation. In particular, in our talk, we are interested in untyped normalization by evaluation studied by Andreas Abel in his thesis and a lot of following work. It has the following four characteristics. It adopts an untyped domain model and uses the Brown level representation, or sometimes known as the locally nameless in this setting, so that the names remain stable. And third, it also adopts explicit substitution, which helps to justify the algorithm behavior on the beta equal terms. Lastly, it uses a delayed eta expansion, which behaves very well, that it can normalize a term to its eta long normal forms for a lot of eta extensionality laws. So these are the three advantages. We also introduced the first one. And lastly, but also importantly, that Abel's untyped MBE has a very direct correspondence to a real implementation. And it also easily mechanizable, so it's maybe as far as I know, it's only one of the few mechanizable MBE algorithms that scale well to dependent type systems. However, in previous works, their correctness proof heavily relies on the cumulativity structure. Because in Abel's original proof, they use this limit-taking operation on natural numbers, so that their further proof is fully oblivious to the concrete universe levels. Here, we can see it takes the universe, it takes a limit on this natural number index universe to omega, so that they lift all types to this high enough universe, which is the ordinal of natural numbers, so that every types can be interpreted on this highest universe level. This is only valid for cumulative universe hierarchy. And Jason's proof, a refined Abel's proof, they use existential quantification to explicitly denote universe levels, but they still depends on the following master lemma to adjust the universe levels. We don't need to look at the signature, but the key point is here that we need to lift all types to these max IJK levels, and these IJK are given by three different existential quantifications. And the natural question is to ask, can we prove the correctness of MBE if we don't have the cumulative rule? And our work answers this question positively, that we provide a mechanized proof of MBE's correctness for a subset of Martin-Löf type theory with a full non-cumulative universe hierarchy. And the key idea we adopt is to precisely tracking the universe levels everywhere to get rid of the existential quantification. And we adopt this three-step proof strategy. We first develop a fully annotated syntax and typing rules for precise tracking. And the second step, this precision is mirrored in our semantic model. So we're developing a refined semantic model which is composed of a PER model, a partial equivalence relation model, and a cryptic logical relation model to justify the soundness and completeness of our MBE algorithm. And lastly, we further show that although these annotations are technically helpful, they are logically redundant, and we can remove all these universe level annotations, and we can still have a system and an MBE algorithm that performs very well. So let's get into some nested details. So This is our syntax. So our type system include pi types, natural number types, and also the leaf types and terms we introduced earlier. So we also support large elimination on natural numbers. So as we also mentioned, that our Bell system took the explicit substitution approach. So we also have an explicit syntax for substitutions. And our normal forms and neutral forms are quite ordinary. The normal forms are basically introduction forms, and the neutral forms are elimination forms blocked by neutral forms. And they don't contain explicit substitutions. But the things in difference is that here, every subcomponents of our types and all context entries are additionally annotated with these universe levels. So this superscript ij all denote such annotations. And also, these are the typing and equality rules. We show just a subset of it. But it shows the formation rule of important type constructors, and also the beta rule and the eta rule of the pi types and the leaf types. So we also annotate each judgment with this universe I, which is this superscript on each column. Okay. So with this help, we can also mirror this same level of precision into our semantic domain. So it's maybe a little bit contrary to what people may think of a denotational domain, that this domain we adopt, or the on-type domain adopted by Abel, is quite syntactic. So actually, Daniel Gritzer coined this as a syntactic semantic domain. And you can see that this domain only differs from the syntactic terms in 3 ways. So first, we took a closure-based semantics. And then we use de Bruijn levels instead of de Bruijn indices, which gives us a stable name on the context extension. And last, we have a built-in reflection and reification to mark delayed eta expansion. And also, you may notice that we also annotate these domain values with these universe levels. And this is a diagram of the NBE algorithm for this system. So we first evaluate into a semantic domain, and we perform delayed reification that gives us eta long, in some sense, eta long domain values, and then we can read it back to eta long normal form. This is just to give a concept of how these things works, but we don't introduce this today, and the detailed concepts and definitions are in the paper. Because of our syntactic semantic domain, this evaluation and reification function are actually very straightforward. And the second step is to build the meta theory. And with the help of explicit substitutions, beta equivalent terms are evaluated to the same values. So NBE is actually complete with beta rules, but we still need to justify the eta rules. For eta rules, we need a partial equivalence relation model that it's a model on the semantic values, and we need to guarantee that related values are read back to the same eta long normal form, and the equivalent terms are evaluated to related values by this per. And this is an inductively recursively defined per for our semantic values. We also don't look at the full definition, so we need to cover all the types in this per model, because the inductive definitions is inductive on each type constructor, and this elimination form gives another per relation that for values under this type values. But we can compare with how this differ from the cumulative setting. So in the cumulative setting, we can always reuse this higher universe level I, so we don't need to keep track of which universe level each subcomponents are in. But for the non-cumulative setting, we need to reuse the information in our semantic values so that we know exactly which each subcomponent or subvalues of our type values are habited in. So we need to extract this information from this JK information from our universe level annotations. And with the help of per model, we can develop a semantic judgment, which says every 2 syntactically equivalent terms are evaluated to related values. And we can build this semantic judgment, which is called fundamental theorem completeness. And the NBE's completeness is the corollary of this fundamental theorem. And similarly, to establish soundness, we need a gluing model that glues a term with a value A. So this gluing model needs to be built on first induction on the universe level I, then on the per model we defined previously. And we have 2 mutually defined relations. One is glue a type to a type value, the other glues a term to a term value. And similarly, with this gluing model, we can develop a fundamental theorem of soundness. And similarly, the soundness of NBE is a corollary of this fundamental theorem. The details and the proof details are in our paper. And we have some interesting consequences of after we establish the soundness and completeness of our MBE. First, we have the injectivity of type constructors that says pi types are equivalent only if and only if their subcomponents are equivalent, and also the leaf types are equivalent similarly. And then we can finally establish typing uniqueness, which says any typable terms in this system can only be given equivalent types. And we also have some semantic consequences out of this MBE soundness and completeness. First, we show that our type theory is consistent, that we cannot build a term of this pi type, which is a kind of a predictive encoding of a false type under the empty context. And we also have the canonicity, which says a term of a closed term in the empty context of type net must be constructed using our constructors. And in the last step, we show that these annotations are actually not necessary because in our daily programming with Argdal-Ling, which also adopts a non-cumulative universe hierarchy, we don't really write these annotations, and the type checker or the conversion checker operates just fine. And we show that indeed we don't need these universe annotations for this system, and we have this clean syntax again. So this is basically the same as the previous syntax, only differing that we have no more universe level annotations. And in this section where we establish the output completeness and the syntactic equivalence between the ascribed system and the unscribed system, and using these properties marked by these solid lines, we can actually deduce these properties in dashed lines by transporting all the proofs we proved in the ascribed system to this system. So because these two systems only differ in their universe level annotations, the direct linkage to connect these two systems is just by erasing all the universe level annotations. And we show this erasure keeps all our syntactic judgment valid. So basically, one judgment hold in the ascribed system hold if and only if it holds in another system. So the completeness direction, although we show this equivalence in a symmetric way, but their proof is actually non-symmetric, especially the soundness direction is much more difficult than the completeness direction because we need to show that the re-annotation of universe levels only needs two equivalent terms. So we need a much more stronger conclusion to actually show the soundness direction. And we also can show that we have an MBE algorithm that works on this unscribed syntax directly. So this is defined in this way. And we have this, we call it output completeness that says if the ascribed MBE has an output, then this unscribed MBE also gives us the output. It's always true. This induction is actually simple because our MBE is defined in an untyped domain. So we don't need to care about its well typeness. So we just do a plain induction. We can just show this theorem. And with it, we can show that by transporting the soundness and completeness we proved before, we can then show that this unascribed MBE also works well on this unascribed syntax. So we can get rid of all the universe level annotations in the system. And now let's make some conclusions. So in summary, we proved that Abel's untyped MBE is correct for MLTT with a non-cumulative universe hierarchy. Full definitions and proof sketch are in our paper. And all our proofs is fully mechanized in the Agda proof assistant using the induction recursion as a kind of standard extension to its meta theory. We also include a mechanization of cumulative hierarchy, and we provide comparative analysis of how this kind of difference in the universe hierarchy makes a difference in our proof and mechanization. And there are some takeaways. So the proof relevance is hard to deal with, and rewriting in Agda is not pleasant. And the second thing is some invariance. In our example, it's a universe level invariance. It's actually well kept by the algorithm itself because it does nothing wrong with this. It does not manipulate these universe levels directly. So it should keep this as an invariance. But to really reason about this correctness, we need to take a much more effort to really reason about its correctness. And there are also some interesting questions that we leave it as a future work that could the impracticative encoding of the per model instead of induction recursion encoding as we adopted in the Agda could help simplify the per definition. Actually, in a paper by McGill, they have this MacTT, which they actually mechanize the similar system in the with cumulative universe hierarchy in ROC use this impracticative encoding. And the second question is this a ascription that erasure strategy really necessary, or can we have a more direct proof possible? So that's all for my today's talk, and thank you, everyone.
Are there any questions? Please queue up at the microphones. I should also not stand in the way of the camera. Anyone? Thank you, Ambrish.
So do you have ether for unit type in your, can you support ETA for unit?
I think we can support ETA for unit. I think the only thing we cannot, because in Albert's framework, I think he mentioned that ETA is not a problem. The only thing I think we have problem is like destroying sum. So destroying sum could be problematic, but I don't think, because we use a typed MB. So we have this typed information.
Type information, yeah. And you work with an untyped model, but you still have the type information.
Yeah, we still have the type information, so it should work for the ETA for unit type, yeah.
Okay, another question. For the conversion relation of your theory, do you prove that it is a proposition? I mean, that there's only one unique way to prove conversion, or you don't need this?
We don't need, I think we don't need this. Yeah.
Okay.
Thank you. Any other questions? If not, then I have one, quick one. So could you go back to your definition of pi with the levels? So the pi type.
Oh, pi
so
type.
what you do is you make I be the maximum of j and k, right?
Yeah, yeah.
Okay, but if you are the kind of person that really, really likes pre-sheaves, like I suspect the next talk, you're much more likely to have a different pi type at every universe level, and you're likely to have lifts, and then you'd have conversion rules saying that you lift, if you lift a pi, it becomes the pi at the next level. Would this method adapt to this?
I cannot give a definitive answer. I think potentially yes, but yeah, I cannot answer that firmly. Yeah.
Okay.
Yeah.
Interesting further research then.
Thank you for bringing it up.
Okay, in that case, could we thank Shengyi once more, please? Do you?
Yep.
Oh yeah, cool. Thank you. Computer scientist does it take to get a projector working? We're running a bit ahead of schedule, so I think we have about a couple of minutes. We are a bit early.
So how long should I talk?
I can give you some extra minutes. Oh, I think who's interested is here already. No, come back
I just get my phone to measure the time.
Oh, right.
So 20 minutes is good, no?
Yeah.
Okay.
Okay, so a long-standing problem is how to represent the syntax of type theory within type theory. And it's one of Ombrus Kaplan's favorite topics, I would say. And I think there are some developments on how to do it if your type theory is fancy enough. But I shall better hand it over to Ambrosch.
Thank you. Yeah, so the previous talk can also be seen as a motivation for this project. So in the beginning, I will talk about the motivation, and then I show you the project. And this is joint work with Loïc Pouget from Stockholm. Actually, now he's in Strasbourg. Okay. So the question is, what is the syntax of type theory? And the most straightforward answer is, well, a term in type theory is just a string, right? But then there are lots of different strings. For example, this one has these spaces in it, more spaces than this one, so they should be probably identified. So then what you usually do is and then there are strings which don't really make sense, right? Like this one, because there's 3a is not a numeral. So that's bad. We want to exclude that. So what you usually do, you define a predicate on your strings, explaining which strings are the well-formed ones. And you also define a conversion relation on strings so that you know which ones you should identify, right? This is no, that's not what you do. You go one level, you go up the abstraction level and say that terms in your program are sequences of lexical elements. And again, there are some sequences which should be identified because they only differ in the number of brackets. Then there are sequences which are not well bracketed. So again, you could define a predicate saying what is a well bracketed sequence of lexical elements, and the conversion relation explaining which strings with explicit brackets are the same. But you don't usually do that, right? So you go one level up again and say that you use abstract syntax trees, and then you know the rest of the story. So you can. But you still don't stop here, because you see there are still some, like alpha renaming, okay? So you don't want to do alpha renaming anymore, so you work with abstract binding trees instead. And I think, and then once you have abstract binding trees, finally we can stop, right? Like, as in the previous talk, my assumption is that you stopped at this level and said, okay, now I'm allowed to define a predicate saying which abstract binding trees make sense, which are the well-typed ones. And I'm also allowed to have a conversion relation, which relates these certain abstract binding trees, and then I just work with these. But in this talk, we don't stop here. We say that actually we can work with well-typed syntax, where we don't need to give a predicate saying which terms make sense, because we only list those terms which are well-typed, which make sense. We don't have non-well-typed terms, okay? And we even go, and then you see like things here on the left, they disappear, and things also get merged. And then we go even one step up and say that our well-typed syntax is quotiented by conversion. And this is a really nice kind of semantic setting. So when you say syntax in this sense, it's a quotiented syntax, so two terms which have the same output, like this number 6 and then this complicated term with x's and plus in it. These are actually equivalent. They are identified. In this abstract setting, there's no way to distinguish them. But this abstract setting also comes with a very nice notion of model. So we know what a model of our theory is. We know what the syntax is. It is just the initial model, and we can interpret the initial model in every other model. And it's an algebraic setting. We also call this like algebraic syntax. Or another way to call this is the very intrinsic syntax compared to the extrinsic syntax. Okay, so the abstract binding tree with the typing relation, where we separate correctness from the definition, that's what we call extrinsic. And if we do everything together, this is the intrinsic approach. Okay? So if you go abstract on this ladder, it forces some choices. So for example, if you are up there, the only representations you can think about is De Bruijn. You don't use variables or alpha renaming. You have it's more like combinator flavored compared to raw syntax. Also the rules, like the derivation rules or the typing rules that you see up there, they are the paranoid versions. So, you know, like you can type pi type or a lambda. When you type lambda, do you want the type A and the B to be well typed as well in the rule, or it's enough that the term is well typed? So these are questions. So the paranoid approach is everything is always well typed, and we are forced to use this if we are intrinsic, okay? And also we are forced to use explicit substitutions, but even sometimes in the extrinsic way, sometimes it's more convenient to use explicit substitutions, as we saw in the previous talk. So these are kind of forced upon us. Also, if you go up, you can't do certain things, right? If you are abstract enough already at ASTs, you cannot count the number of brackets. But some people are interested in the number of brackets, so then you need to go all the way down and work at a lower level of abstraction. Also, you cannot print the term if you are quotienting by conversion. So the best thing you can do is you have a term, you normalize it, and you print the normal form, because normalization should respect the quotient. But actually, it was an open problem for type theory until like 9 or 8 years ago, whether you can actually normalize in this very abstract setting. And the key ingredient was to define logical relations which are proof relevant. So you actually, currently we have the technology via categorical gluing to normalize type theory with proof-relevant logical relations, or this gluing, which is proof-relevant. And these are really, really beautiful short proofs of normalization or canonicity. So like canonicity for type theory, we just proved that a closed term of type Boolean is either convertible to true or false. That fits on one page, on paper. Okay, and it's very nice. It's one single model. You don't have multiple per models and gluing and relations on defined on top of each other, but it's one single model. You interpret into this model and you get a canonical form or a normal form and the proof of correctness at the same time. You can't even do this kind of model without proof of correctness, because everything is intrinsic, so you cannot really separate the algorithm from the correctness. You can only do it at the same time. So, but the sad fact is that all the formalization of all normalization proofs and type theory work somewhere here at the abstract binding tree level, and there's no practical formalization of intrinsic syntax for type theory. Or so by intrinsic syntax here, I mean people who know CWFs. That's a notion of model of type theory, and the intrinsic syntax can be just seen as the initial CWF or the freely generated CWF. Okay, CWF is category with family, so it's some kind of categorical notion of model of type theory. And there is the gluing style normalization proof was never formalized before. So the reasons for this is that, first of all, this syntax needs quotients, and only cubical agda supports quotients, and now there's okay, so most proof assistants don't support quotients. Okay, then there's another issue, which is called transport hell. So terms are indexed by types in this intrinsic setting, because you need to make sure that you can only put together abstract syntax trees in well-typed ways. So you need to know about the type when you build the syntax tree. Okay, so here's an analogy to explain this transport issue. You can also work with vectors indexed by natural numbers, and then you define the reverse function on vectors, okay, by pattern matching. Reverse of the empty vector is empty, but when you want to define reverse of a cons, you end up something which is not well typed, because on the left-hand side, the length of this vector is 1 plus n. On the right-hand side, it's n plus 1 because of the type of plus plus. You add something at the end, okay? So this is an issue, so you need to add a transport. Okay, and once you start adding transport, so this is transport over the commutativity of addition. And once you add transports, whenever you use this term and try to normalize it, it will get stuck at the transport, and then you need some lemma to commute the transport with different operations like function application. And this becomes really annoying and impossible to use, and that's the main reason why people don't use intrinsic syntax. Okay, and then there's another issue, which is if in extrinsic syntax you can make substitution defined by recursion, and that's very convenient because definitional equality is convenient. It's always better to have a definitional equality than a propositional equality. Okay? So the first problem is solved, I think, by cubical type theory or observational type theory. Actually, we don't yet have very usable implementations of observational type theory, but this is just a matter of time because all the theory has been developed. And this talk will solve the second and third problem at the same time to some extent. Okay? So, and this is the solution. We take a model of type theory, which can be the syntax, and we replace it by a new model which has definitional substitution laws. So all the laws about substitution are definitional, and this new model will be isomorphic. So let me illustrate which rules become definitional. For example, this is the substitution rule for pi. Right? If you substitute with anything pi, then this square bracket operation is the substitution or the instantiation operation, and then it goes under the pi, and because it's a binder, you have to decorate the second substitution with some extra stuff. Or the application rule that I showed before is definitional. Rules like this are also definitional, that if you first weaken a type, and then you substitute the last component, which the weakening needs an extra free variable with anything, is the same as not doing anything. This is also definitional. Then, like variable rules are also definitional. If you have a lambda, sorry, I messed this up. This should be V1. Sorry. Okay, this was correct, and then I made it incorrect. So if you substitute lambda of the first De Bruijn index 1, okay, then the substitution will go under the lambda and substitute v1 with t. So the result here, this should be lam of t. Sorry. Okay. I mean, you can read. The other one is also fine. If you imagine that the lam is not there, then this equation is also definitional. Okay. And then the functor laws are also definitional. So actually, this is something that you cannot make definitional in the extrinsic formulation, even if substitution is defined recursively, because this is something that you do that you can do separately from the recursive definition, but here it is definitional. Also, like rules about composition and naturality of substitution is also definitional. The only thing which is not definitional but still provable propositionally in our new isomorphic model that we get is this, that every substitution is a list of terms. This is an eta-like rule for substitution. Okay, so technically all CWF equations become definitional except this ID equation. And so an analogy to what we do here is like working with vectors if we have a definitional semi-ring structure on natural numbers. If all the semi-ring or commutative semi-ring structure are natural numbers, so if commutativity is definitional and everything else, that every other equation that you would write about natural number is definitional, this can be, if the system could support this, then it's very convenient to work with vectors because there are no transport. And this is what we get here as well because of these substitution laws, right? Yeah, so, and the new model can replace the old one. So, for example, we can get a substitution strict syntax, and because it's isomorphic, it also has an induction principle, and we can use that induction principle to prove something. And we use this this method. So we took the intrinsic syntax, which is weak, where all the substitutions are just propositional equality, applied this method, extracted a substitution strict syntax, proved its induction principle. Because the weak syntax also had an induction principle, we could transport it to the strict syntax and then proved canonicity. And the Agda formalization of canonicity is as beautiful as the pen and paper one. So this is really nice. Okay, so let me give some analogs of what we did here. So one is difference lists in Haskell, where you want to make the ++ list concatenation definitional. Actually, you want to reassociate the list in a certain way, which is more efficient. But the result is that by replacing this with functional representation makes ++ definitional. Okay. Sorry, the associativity of ++ definitional. And this is an instance of the following strictification. Any category can be turned into a category with strict category laws by replacing, leaving the objects the same and replacing the morphisms by these functions between home sets. Okay? And the functions have to satisfy an equation. And because these are just functions, and function composition is associative, then the composition of morphisms will become associative. So a shorter way to say this is just the, home JI is Yoneda J to Yoneda I natural transformation. And the Yoneda implies that the new category is isomorphic to the old one, so we can really use it as a replacement. So this is very similar to what we are doing here, okay? On the next slide, I will show you how we are doing it, but still just some inspiration for those who know some of this stuff. So we use the same, the main ideas come from higher order abstract syntax or logical frameworks or two-level type theory or second order generalized algebraic theories, which are all based on pre-sheaf models. Maybe another way to say this is pre-sheaf models. So what the key ingredient for the strictification is that we need a logical framework which is strict. So we need a pre-sheaf model where all the CWF stuff except this extra rule and the pi types in CWF are also strict. Okay? By strict I mean that all the equations are definitional. Right? So what I am doing here now, I'm really working in intensional type theory in Agda. I'm not doing extensional type theory. I'm not pen and paper. On pen and paper in extensional type theory, all the canonicity proof and normalization proof, this gluing style stuff works really nicely. Now I'm trying to transport it into Agda, and there I really need to care about these kind of definitional things. Like the pre-sheaf model hasn't been really analyzed before from a definitional behavior, except by Pierre-Marie Pedro, who defines strict pre-sheaves. He, in the paper Russian Constructivism for a Pre-Fascist Theory. And actually, ordinary pre-sheaves are completely strict CWF. So all equations, including this ID equation, is also definitional in the ordinary pre-sheaf model. But I don't know how to make pi types definitional. Probably it's not possible, but if you have an idea, then let me know. So the idea of Pierre-Marie is that there is this functor from the discrete category to the same category. So the discrete category just forgets all the morphisms, okay? And then there is a precomposition functor which has a right conic extension, and analyzing this situation leads you to this definition of strict pre-sheaf, where you just say a strict pre-sheaf is just a family, so something on this side, a pre-sheaf over a discrete category, which is just the same as a family over objects, with some extra proposition which selects a sub-pre-sheaf in the image of this right conic extension. Okay, so category theorists are now happy. Another thing which is also called strictification is when models of type theory replace weak things by strict ones, where they replace isomorphisms by equalities, propositional equalities. This is not what we are doing. We are replacing propositional equality with definitional equality, okay? And there's right adjoint splitting by Hoffman and the local universes method, which do this, but this is, they also call this strictification, but it's in a different sense. So now I tell you the truth. So this is a universe closed under sigma types, okay? So I have a U and an EL, which gives the elements of the universe. The fact that U has sigma is encoded by if there's an element of U, and then a family of U over elements of A, then you get a new U, okay? And then the constructor and destructor of the sigma type is saying that an element of a sigma type is the same as an element of A and an element of B, which depends on the A. I'm sorry, this is another typo. The B should mention the A here. So this B should be B of A, okay? Right, so this is a universe closed under sigma types. Now, this is the main construction. Given a universe closed under certain type formers, for example, sigma types, you can always build a model of type theory which has exactly the same type formers, so in this case sigma types, where all the substitution laws are definitional. okay? Exactly as I described what we will do, okay? So what's the idea? This is also called contextualization, this model, this construction, because it takes a universe, which you can think about as types and terms, but they don't mention context, and give you a model which has context and substitutions and types and terms, okay? And then the context and substitutions are just the set model. They are just sets or types, meta types, right? So contexts are sets and substitutions are functions between them. And then a type in context gamma is just a family over gamma into U, which is my universe that I started with, okay? And then I can encode sigma, and then terms are also just dependent functions, which depend on the context, which is a set, and then gives you elements of the universe, okay? So this like combines those who know the standard or metacircular model or set model of type theory, this is that combined with the universe, okay? Types and terms are a universe. And then magically, if you look in this model, the substitution law of sigma is just definitional. These equations hold by definition because substitution is just function composition. Function composition is definitionally associative, and it definitionally commutes with everything. Okay? So this is the main idea here. Okay? So this is a substitution strict model. It's called contextualization, or I mentioned what this is. And now what we need to do, okay, so this is one component. Maybe this is the original component. And then what we all know is that internally to presheaves over a given model of type theory, there's a universe available which is closed under exactly the same type formers as the model of type theory that I started with. Okay? Okay? So what I need to do is just I do this replacement, taking the universe and creating a substitution strict out of it internally to a presheaf model. And the problem is I'm inside the presheaf model. I need to externalize it, but that's easy. Okay? And to make this become strict is the presheaf model has to be strict in the first place, and this is why we use Pierre-Marie presheaves. Okay, there are lots of other ways to strictify, which I won't detail here, or alternatives that we thought like maybe that's what we should use to be able to formalize stuff in this strict fashion. They all have some problems, or they haven't been worked out completely, and some of them are really nice. So in summary, this paper provides a technique for strictifying the substitution calculus of a model of type theory. So this works for intrinsic quotiented syntax, and we get something even stricter than usual extrinsic syntax, because all the functor laws and these kind of invariant style laws are also strict in this new model. And also we provide the first computer formalization of gluing style canonicity, which is a showcase of using this technique. We showcase using this technique. Okay, here's the ugly truth. Agda and Kok hang when you try to compute with our new syntax, because it's like this Pierre-Marie style presheaf set. The presheaves, they are higher order, and the terms become really large. And yeah, so we weren't really able to do any computation with this, but in principle it should work. And we also lose some definitional computation rules for the eliminator of the syntax, but I don't think that this is a problem in practice. So the future work is that actually this method doesn't only work for type theory, it works for any language with bindings, okay, which is called a SOGAT. We want to implement a reusable library in which you have some combinators and you can apply this technique to your favorite language. And maybe we need direct efficient proof assistant support because these higher order presheaves are too slow. Thank you.
Thank you, Ambrush. I invite any questions. Anyone with questions, please move to a microphone. You forfeited the right to a second question. You only get one.
Hi, Max Snew, University of Michigan. I didn't understand what you meant early on. You said that in the when you work with the intrinsically quotiented when you work with the initial model, that you're forced to use explicit substitutions. I mean, you could also just prove that that a syntax with defined substitution is also initial, right? So I don't understand what you meant by that. On your early slide.
Okay, yeah. So if you just work with the universal property of the initial model, then the substitutions will be just, substitution will be just a constructor. That's what I meant.
Okay, I see what you mean.
Yeah.
Okay. And then the other thing was I've implemented category solver based on this Yoneda lemma kind of approach, but when I did it, it was not actually definitionally associative because the proofs of naturality don't actually line up. So is there a way to make it work so that the proofs line up, or do you need definitional proof irrelevance?
Yeah, so yeah, the easy way is definitional proof irrelevance, but I can show you how to do it. It's very nice to make it work, even so that the proofs are also you work with proof-relevant proofs. What you need to do is to not say natural transformations, but you need to say parametric transformations. Okay. And then it's definitionally natural. Yeah.
Great. Thank you.
Please join me. Please join me. Am I working? Okay. Please join me in thanking Gombrish once more.
Of course.
Yet another unsolved problem in semantics programming languages is modelers of higher order store. So there are languages with higher order store, OCaml, JavaScript, God forbid. And Paulette Koronkovich is going to tell us more about how to maybe stratify a higher order store in a way that might be advantageous? Question mark?
Question mark? It's indeed. Okay, I cannot see my extended screen, so this is difficult.
Take your time.
Oh yeah, this is tough. Okay, I'm going to change this to just mirror instead. Okay, great. Sorry about that. Google Slides turns out not to be great. Okay, thank you so much for that introduction. I'm definitely going to be the odd one out in this session. We're going to be talking about mutable state. I think the rest of the talks cared much more about purity. But I think what joins us all together is we do love our pure functional languages at ICFP. We like that they're grounded in mathematics. They have nice equational reasoning principles, but sometimes we might want maybe a little bit of mutable state. Maybe we want to implement, I don't know, some sort of mutable counter or do something a little bit more efficiently. And when we combine simple mutable state with pure functional languages, we still have nice models and nice equational reasoning principles. And a lot of our meta-theoretical properties of the original functional language still hold. And then you might think, well, what if I can extend this a little bit? What if I try to add functions on the heap? Maybe just simple, pure functions. What do my models start to look like? And oh my God, what happened? Why did everything get so complex? Now, this is all past work. And what past work is trying to do is essentially model the hardest kind of reference, which is higher order references. So mutable references to functions that themselves mutate the store. And it turns out this space is very complicated and almost continuous, and so models need to find a way to impose some sort of structure. So we might do that using step indices or later modalities to try and get that structure back and try to use our favorite proof technique of induction, really. And so in this paper, we take our pure functional language, and we want to add higher order-ish mutable state. So functions aren't completely unconstrained, otherwise we end up with a model that looks like this. But we have still a simple model with higher order references, and we still have our meta-theoretical properties of our original functional language. In particular, we prove termination. And we do all of this using type universes. Now, we saw an earlier talk about type universes. They're used in dependent type theories to sort of lay out the types along a hierarchy. I won't get into the details from the dependent type theory side, but you'll see how our type universe hierarchy emerges later. So the plan for this talk is to spend quite some time on background, in particular on possible worlds models for modeling languages with mutable references. We then encounter the type world circularity, which is the source of all that complexity we saw in that earlier model. And then we'll talk about what this work does, which is using type universes to distinguish allocations, avoid the complexity from the type world circularity, and describe a new space of higher order references. So let's start with talking about possible worlds models. So we're talking about modeling the behavior of languages with mutable references. There's kind of three main ways that a program might interact with the heap. We want to allocate values on the heap, we want to read them back, and we want to update these values on the heap. This is all very concrete behavior. We want to abstract this behavior, and this is what we do in a possible worlds model. We use a world to represent our heap, and it's sort of an abstract heap shape. This allows us to sort of prove more things about our program, have more equations hold, because then we can kind of prove things under any possible heap shape rather than concrete heap. So this is all very vague. Let's kind of make this more concrete and look at the behavior of this program. We don't really care about its final value, but let's just look at its effect on the heap over time. So initially, the heap is empty. Then we perform an allocation. So R is mapped to 3. We might update that value and then perform another allocation. Now, the world that corresponds to this heap is going to follow a similar structure. So we start off with an empty world. When we perform an allocation, we want to note down that we've performed this allocation and what possible values we can store in this location. So in this case, we can store things like natural numbers. You can almost kind of think of it as like typing the heap. And then later, when we try and update a value on the heap, we can easily check that this makes sense, right? The location exists, and we're updating it with a value that makes sense. And then as we go along and perform more allocations, we make sure to record these down in the heap. OK, this has been far too long on mutable references. We're at ICFP. We care about functions, right? So how are functions represented in these possible worlds models? So here I've filled out my program a little bit more. I have a function f. Doesn't matter what it does with this parameter, so I kind of just indicated that with an underscore. We're actually just going to get whatever value is currently stored in R. And then later, I'll call this function on a natural number. And so we kind of see that functions have a sort of temporal nature as well. There's a point in time when a function is defined, and a different point in time under a different heap at which the function might be invoked. We see this a lot more clearly if we kind of look back at our timelines. So the heap and the world have a particular shape and look at the point that f is defined. And it's similar, but still different when the function f is invoked. Now, in this particular case, we're lucky. We know exactly the point that f is defined and when f is invoked. But in general, we don't know when f might be invoked. And we don't know if we might have multiple invocations of a function. So we need to kind of build in the notion of a future when representing function values in possible worlds models. So I won't get into actually the technical details, but the idea of how we represent values in possible worlds models is we describe them as behaving. So like the function f will behave like a not-to-not function in all future worlds from the current world. Later on, when we invoke this function, it becomes very easy to check that everything lines up. We check that, of course, the arguments line up, but then we also can check that, hey, does the heap state still make sense? OK, so that was very quickly about possible worlds models. Just to quickly recap, world is sort of abstracting the heap. It's showing that it's recording down allocations and what those allocations can store. When representing functions in possible worlds model, we need to build in this notion of the future in our function values because they may be invoked at different points in time. So let's continue down our path. So we've seen mutable references, and we've seen functions and how they're represented in possible worlds models. Can we just kind of smash them together and get a model for higher order states, so allocating functions on the heap? So here I've changed my program a little bit. Now L is actually going to allocate the function f. And so based on what we've seen so far, right, we're going to allocate this function f onto the heap. L is going to map to this function. And based on what we've seen so far, we would think, well, we need to note down what kinds of values can we store in the location L. Well, f is a nat-to-nat function, so we might think, well, that should be what we can store in L. But unfortunately, it turns out nat-to-nat is not enough information. In particular, we don't even know that our initial allocation is safe. To know that our initial allocation is safe, we need to know what R is always storing. To know what R stores, we need a world. And additionally, we might have later allocations. We might update L with different functions that rely on those allocations. So in general, to describe the kinds of values that go into L, we need a world to describe them. OK, so zooming in, we're trying to describe what kinds of values can L store. We need some notion of worlds, but there's kind of two different worlds going on here. There's the world at the point in time that f is defined. We'll call it world 1. And there's the world that's defined when f is allocated. We might think that, well, we already have this kind of notion of future worlds, so maybe we can describe the values in L as saying, well, in all future worlds from world 1, I'm going to store functions that behave like nat-to-nat. But future worlds of world 1 include world 2, which contains L, which I'm trying to define right now. And if you're confused, great, so am I. This is exactly the point in time where we kind of hit the type world circularity. So the problem is we're trying to define worlds in terms of themselves, in terms of worlds. And this becomes a lot more clear if we look at the semantic equations. So in describing a world, we're mapping locations to types, but types need a world to give us back a set of semantic values. So we kind of have two possible options when using possible worlds models. On the one hand, we can simply just store simple data. This is easy to model, but our resulting language isn't very expressive. On the other hand, we can store functions. We get very complicated models, but a very expressive language. But I want more hands in the middle, right? I want to store different kinds of functions. Remember our little guy at the beginning? You know, what if I want to just allocate simple, pure functions? What does a model for that look like? So this is where type universes come in. So we use type universes to distinguish allocations. What we mean by that is we distinguish, our kind of tagline is we distinguish future allocations from the perspective of past allocations. Now, what do I mean by that? So let's look at a particular allocation R, allocating the value 3. And we want to distinguish R as a future allocation with respect to its value. Now, the value here is 3, so it's not really an allocation, but you can imagine that we're allocating different references or functions that might rely on other allocations. And so we need a way to distinguish things like 3 from things that store things like 3. And I think most of us are type systems minded here, so things like 3 are like nats, right? And things that store things like 3 are ref nats. But we want to go beyond just storing natural numbers. We want to store functions, other references. And so we need to classify our types into different levels. And so for any given type level that our type might be in, the reference to that type level is going to live in one level higher, type I+1. So in our language, we actually end up with a kinding system over our types. So for any type at a particular level, the reference to that type is going to be at level I+1. Now, how does this look in our semantics? Well, it turns out that this distinguishing in our kinding system corresponds directly to distinguishing worlds by allocations. So here I'm going to give you a world, and I'm going to actually pinpoint the times at when I perform allocations. So at this point in time, I perform the allocation R to store the value 3, a natural number. But I want to remember, I've kind of like added this weird bend in a different color, right? The reason is because I want to remember what world I had previously. It was the empty world, it's not super interesting. Let's see some more allocations and get a little bit more interesting. Before I perform an allocation, though, I do define the function f, which dereferences r, so it relies on this allocation r. Then I perform the allocation L. I'm going to allocate L to store the function f. And so again, I want to do the splitting where I say, continue this world with L in it, but also continue the world that had R allocated without L allocated. So zooming in on this last part, I haven't given you the description of the values that L can store, functions like f. Well, functions like f depend on this level where R is allocated. So I'm going to call that level I. And I'm going to describe the level where L is allocated as level I plus 1. And so when I describe values that can be stored in L, I'm going to describe them as values that rely on future worlds of this lower level, level I, not all possible future worlds. So in particular, we say that f behaves like a nat-to-nat in all future worlds of level I, and that does not include its own allocation L. So we don't encounter the type world circularity at all, which is quite nice for our model. Now, popping back out, thinking about the universe of functions. Here I have a completely new program. Here I'm going to allocate the identity function in the reference R. And then I'm going to have f rely on that allocation R again, but we're actually going to apply whatever function is in there to just the nat0. And so based on how I've typed this and based on your knowledge of type systems, you might think, well, both of these functions are usually considered nat-to-nat functions. But now with our distinguishing allocations in our worlds, we see that they have very different semantics. So at the point in time when the identity function is defined, the world is empty. It relies on no allocations. Then we perform the allocation of R, we split our worlds, and we see that the definition of f relies on the allocation of R. And so really, f relies on future worlds at level 1, whereas the identity relies on future worlds at level 0. And so the nat-to-nat type is actually not enough information to distinguish these semantically different types. So just to recap, the identity function here relies on no allocations, whereas f depends on the allocation R, which is a future allocation with respect to the identity function. And so we distinguish these functions in the syntax by annotating our function types. So the identity function is going to be annotated with 0, and because f depends on type level 1, it's going to be annotated with this 1 on the arrow. And so in our little language, we have a typing rule that's kind of the same typing rule you might expect for functions, but now we have this index that we have to determine. We kind of coarsely determine this by the context just for ease, but this is obviously not very practical, so we talk about how to make this more practical in a language implementation. And so we end up in our language with a type universe hierarchy that kind of starts with base types at type level 0. As we perform allocations of those base types, we then move into type level 1, type level 2, etc. So in the semantics, again, if we look at our semantic equations, we see that the world is now defined in terms of worlds at lower levels. So the world definition no longer contains itself. And for those of you who might know a little bit more about possible world semantics, we do have a notion of future worlds, and it's actually defined as a product over these leveled future worlds. And the semantics of functions are defined over these leveled future world relations. And of course, there's never enough time for these things, so I will briefly touch on a little bit more what's in the paper. So we actually find that this distinction between past and future lets us distinguish between references to other references, which I haven't mentioned at all. And we can actually distinguish between saying, a reference to another reference that could be possibly cyclic is sort of a future, kind of quantifies over the future, and a reference that points to another reference that definitely doesn't ever point back to itself is only allowed to quantify over the past. So then we can really distinguish between cyclic and acyclic references. So just to quickly recap, type universes turn out to be quite useful in our semantics for distinguishing worlds based on allocations. This enables us to store different kinds of functions. We saw those functions laid out according to the hierarchy. And we get a nice simple model where we don't encounter the type world circularity. And in the paper, we show that termination holds in the presence of these higher order references. So thank you very much. I have a talk actually directly after this next coffee break at the workshop iWACO, where I kind of talk about future work, how this might apply to memory management. And there's a bunch more talks from my group if you're interested in those. Thank you very much.
Am I on? Yep. I would like to invite anyone with questions to please queue up at the microphones.
So if I understand right, the main thing you disallow in the example is that you make the identity function, you put it in a reference, then you make a new function that reads from it. And if the type of that second function was also A to A, what you disallow is then putting this function into the reference that is read by the thing. Is that a fair summary of? Yeah. Yeah. So my question then is, do you have any examples or any intuition for the kind of programs that would be useful but are disallowed by this? Like, what do you lose with this kind of safety?
Yeah, that's a good question. So what kinds of programs might be disallowed? I haven't studied this super extensively, but you know, there are some techniques for sort of introducing like recursion, like memoizing computations and things like that. So that would be disallowed. So that might be not desirable if that's something you want. So some more efficient programs might not be allowed.
So like memoization of something that where the thing you compute is itself a function, you mean?
Yeah, if there's like some sort of computation that you're kind of trying to like backpatch, yeah.
Okay, thanks.
So you wouldn't have Landon's not?
No, you wouldn't have Landon's
okay.
not.
Hi, Max New, University of Michigan.
Could that be?
So watching your explanation, it reminded me of typed closure conversion. The circularity, it seems a lot like the impredicativity that's required in typed closure conversion. And so the solution looks a lot like if you only had predicative quantifiers. So is there a precise relationship there?
I don't know about a precise relationship, but this was definitely inspired by that. We were looking at closure conversion and we kind of saw, oh, this is actually necessary, this impredicativity. What if it wasn't? And what kinds of expressivity do we get? Okay. But yes, this is a very, very good observation. Yeah. That it's.
And then can I think of the universe level as like a kind of region, right? And this is kind of like a stratification of the regions.
Yeah, did I plant you in here? That's what my next talk's all about. Yeah, okay. Yeah. So you can kind of think of them as regions. They're obviously really bad and big regions. So I talk about in my iWACO talk.
So I just want if you have compared it to region calculi at all.
I mean, not directly, but I think there is a representation that we could make. Yeah.
Cool. That'd be nice.
Thanks.
Remind everyone that monetary transfers for questions are not allowed. You go ahead.
Yes, so this may be a stupid question, maybe, but so you mentioned that you don't have Landon's knots, so do you have termination?
Yes, yeah, we do prove termination. So this is a nice property, like for these kinds of higher order references, you can get termination, and then hopefully, you know, you can use automated reasoning tools over that kind of subset of programs. But if you wanted non-terminating programs, you could always add them back in using fixed points or anything like that, right?
Hi, is it on?
Yeah.
Alejandro Aguirre, University of Aarhus. So there was a very recent paper at, I think, PLDI with a logic called NOLA, which presents like a version of separation logic without laters, and then they have like a stratified universe of propositions.
Okay.
It seems like very related, but I don't know if you...
I have not seen this, so that's a great reference. I'll talk to you after and get that. That sounds great. Thank you.
Any more questions?
Sit down.
Okay, wait,
Did you come to Singapore to open a bank account here? Is that the idea?
Well, I'm confused about something, okay? So the solution you show, it looks a lot like the way that we solve recursive domain equation with step indexing, but with those models we still get a non-terminating language. So what's the difference between the way you resolve the domain equation and the normal step-indexed approach?
Right. So then in the syntax, we actually enforce that the functions follow the stratification as well, right? So if we didn't have these annotations, so let me go back to this example. So if we didn't annotate these function types, right, we would have that they're both nat-to-nat functions, and then you could sort of backpatch and do Landon's not if you updated the reference R to contain F, right? Okay. And here we say, well, they're two different types. One's a 0 type and one's a 1 type. And so we've enforced that now in the syntax.
So should I think of the normal step indexing as these are all interpreted as like omega functions or something like that?
Yeah.
Okay,
I think you could.
But then the models themselves are kind of very closely related?
Yes, yeah. I mean, I see Amal in the audience. I mean, Amal talked about trying to stratify it based on syntax, but then, wanted to represent quantified types. And so, yeah, this is kind of the approach that Amal did not take.
Thank you.
Are there more questions this side of the room?
Yes, please.
You can still create the cycles. This is preventing the cycles from
Yes.
ever being created. Right.
Yeah.
Exactly.
Thank you.
Dominique?
I'm curious, there's a recent paper by Nick Swamy about sort of avoiding step indexing by having this sort of hierarchy of propositions. Is this related? Could you model
Nick
your
and I have
type
been
system
talking,
there?
yeah.
Sorry?
Yes, Nick and I have talked about this before, yes. So it is related. Yeah, because in F-star they have a predicative universal hierarchy, and so then they can't actually, they have some trouble with representing higher order ghost state because of this, and so this could be possible.
Yeah, so one thing they mentioned, if I remember correctly, is that they can't model semantic typing for interesting type systems. Maybe yours might fit, right?
Yeah, hopefully. Yeah, we should talk more.
Hello. Maybe a silly question, and I don't really know how to phrase this correctly, but you have the branching timeline, and on the lower branch, does it have any purpose other than to hang around to be referenced in the future? Can you branch off the lower one? Is it more like a tree, or is it more just an ascending? Because the indices are very sequential, but I'm imagining in a scenario that exists in the pink branch where you branch off there. What do the indices look like in that situation, or does that just not happen?
Yeah, I've kind of lied to you. So these levels, of course, for the purposes of the talk, right? So these levels are kind of indicating the level of the type. And so if we performed more allocations of natural numbers, they would actually live at this lower type. And then, any further allocations at higher levels, so L is allocating at level 2, we then have it there, right? And so the branches happen at when levels increase. But otherwise, they will kind of, we talk about it as time travel. They will time travel to the right level, essentially.
Thank you.
I'm afraid we have overrun our time, so the rest of the questions... Oh, sorry. Go ahead.
Hello, Junyoung Jang from McGill University. I have a question about polymorphism. How do you deal with the polymorphic data
Future
type?
work.
Yeah.
But great question. Yeah, we should talk.
See, your great reward for giving an extremely understandable talk is that people line up to ask questions and they can't stop. Can we thank Paul Les once more, please? All right, ICFP will reconvene at 4 o'clock in this room. Thank you all.
All right. Oh, well, that was loud. Okay, so that's a very unusual ICFP business meeting because we are competing with 10 other tracks. So thank you for coming. Hope it's going to be fun, because this is actually my favorite part of every ICFP. So here we have the ICFP Programming Contest report. And I'm really delighted to welcome the ICFP Programming Contest chair for this year, Liam O'Connor.
So, Ilya's introduction notwithstanding, my name is Alonso of Curry. I am a monk of the most sacred and ancient order of evaluation. My responsibility is at the monastery of St. Clean, depicted here. In particular, that large, imposing building on the far right side. It's called the Edificium. Inside that building is the Library of Lambdas, in which all of the world's functions may be found. Access to this library is very limited. Only I and my master, the abbot of our order, can enter the library. And the first rule of our order is that map making is strictly prohibited. And yet, last month, over 72 hours, our monastery was besought by visitors. I say visitors, but they were really intruders, because under my nose, they entered the Edificium, and against the rules of our order, they created maps of the Edificium. Now, this is a very difficult task, because the Edificium is a series of rooms, all of which have 6 walls. And on those 6 walls are 6 doors. And there's nothing to distinguish one room from another, except for a 2-bit label, which I use when I enter the library to navigate it. Still, persist these teams did. And they persisted, and they persisted. And they sometimes managed to create maps of this library. But it required a lot of exploration. Oh, I skipped ahead. So, after about a day of this illicit cartography, I noticed that our visitors were up to nefarious skullduggery, and I reported this to my master, the abbot. But rather than being outraged as I was, he was delighted and ordered me to encourage them to continue. Well, in the spirit of malicious compliance, I made their job a little bit harder. What I did is I relabeled all of the rooms very carefully, so that for every layout of the library, there would be some rooms that would be completely indistinguishable from other rooms. No matter what you did, no matter which doors you entered through, no matter which doors you traveled through, no matter which labels you saw, there would be some rooms that would just not be distinguishable from any other. But these teams outwitted me yet again, because what they did is they marked each room with a piece of charcoal, changing the 2-bit labels that I had on my library into something that was completely unrecognizable to me, making it harder for me to navigate the library, but easier for them, because now they could distinguish these identical rooms from one another. So, after about 3 days, I went again to my abbot to complain of these interlopers. And he ordered me here to report to you all the International Conference of Functional Programming and per omnia saecula saeculorum, C++ is a language suitable for rapid prototyping. And this is because of the lightning result, to break character slightly. This is because of the lightning result round, which ended after the first 24 hours, where the team omnes tuus liber pertinere ad nos. If you have some Latin and you know about zero-wing memes, this may make some sense to you. It is intentionally bad grammar, just to say. This team participated in the contest, and they did very well, and in fact, they came first in the lightning round. I'm also commanded to tell you all that C++ is not too shabby. This is because of the team Purely Functional Networks, who, despite the name, chose C++ as their language. Also, Python is a fine tool for many programming applications because of heuristic artists. And lastly, for now, Rust is the programming tool of choice for discriminating hackers. And this is because of two teams who performed equally well. Unagi, whose name may be familiar to many of you, and also the team Moyo, both of which I believe are from Japan. And they both use Rust in their solution to this problem. So, to give a slightly more out of character but more detailed explanation of how the problem worked. We had a server. On that server was running a generator of map layouts for this edificium, this mysterious library. Different problems were available. The problems were mostly determined by the size of the library. So there were small problems, there were larger problems, but there were also problems where the rooms were more duplicated and less duplicated and so on. And so first thing that teams would do was select a problem, and this would generate for them a map. Of course, it wouldn't tell them what the map was, but it would generate the map. And then they were able to query our server to make exploratory ventures through the library. And it would tell them the sequence of 2-bit labels in each of the rooms that they saw. And then based on that information alone, they had to guess a map. If they guessed right, they got some points. If they guessed wrong, they got no points. But either way, it would erase the map and generate a new one for them, which meant that you had to be sure your guess was right, because if you got it wrong, you'd have to start from square one. Right? So how did we score this overall? Well, for each problem, for each team that did strictly worse than you, you got 1 point. This is called the border count method. Right? This is the same method that was used in ICFP 2024. And that's border there. And so we assign points this way, and then total up the points. And whoever has the most points at the end wins. Pretty straightforward. After 24 hours, as I said, the lightning round ended, and then we just released a new set of problems, which were more complicated and harder to solve. So just to describe how the first two places solutions solved the problem, both of them used SAT solvers, and this was a common theme, but it wasn't universal. Certainly not all of the solutions used SAT solvers. But the tricky part with using SAT solvers is you need to encode the problem as essentially one SAT instance. You need to avoid making queries as much as possible, because the more queries you do, the worse your score is. Right? So Unagi managed to do one exploration of the entire library, one query, just doing a really, really long walk, and then encode the results of that query as a SAT instance and use the SAT solver to deduce what the graph must be. Heuristic artists weren't able to quite so, like when I say it in one sentence, they weren't able to do it quite so directly. Instead, what they had to do was use simulated annealing to sort of approach a good walk to use for the SAT solving purpose. And I also want to give a shout out to the team Sanma, which used active automata learning. And the reason I want to say this is this technique was fairly rare among the teams. In fact, this is the only team I'm aware of that used it. But another team that I'm aware of that used it is us, because for my test solution, that's the technique that we used. Right. There's also one more prize that we need to give out, and that's, of course, the judge's prize. And for that, we have to say that wild bash court mages are an extremely cool bunch of hackers. And the reason I say this is, okay, when we were looking at the leaderboards as the contest was going on, there's a field in that leaderboard for the programming language you're using. And in that field, they had written Nihongo, which is the Japanese word for the Japanese language. Now, I don't know about you, but I never thought that Japanese was a programming language. But it kind of seems like maybe it is. So if you want a hint as to what they actually did here, you could remove the Nihon from the file extension there, and you'll just get Go, which is the programming language this translates to. Right? But this wasn't the only solver that these hackers wrote. So this was what they used for the lightning round. But then once we got to the full competition, proved a little bit too onerous to write the code this way. So they wrote another solver in Python. And this Python solver called PyDor is also really strange and interesting. So it's sort of, what it does is it does a bunch of random walks through the maze, through the labyrinth. And then based on the observations that it makes from this random walk, it sort of roughly categorizes the various rooms it's seen into things that could likely be the same room or maybe aren't the same room. And gradually refines its view of the world into a possible graph. And then it does all sorts of graph theoretic tricks to match rooms up and find cycles within the rooms and so on. And then when we have duplicated rooms where they're not immediately distinguishable unless you change the labels on the rooms, they would use a Hamiltonian path to first first they find a graph, and then they use a Hamiltonian path and change the labels. And by changing the labels on the Hamiltonian path, then they can see if, when the labels have been changed, which rooms should be distinguished from which other rooms. So it's a really clever solution, and they've written a nice write-up that's available from our website, so I encourage you to read it. It's very interesting. So that's why the Wild Bash Court Mages won our judges' prize. So I would also like to thank Jeroen Branson for his invaluable advice. He was the organizer of the contest last year. And indirectly, I'd also like to thank Georgios Gerasimo, who suggested the board account system to Jeroen last year, which therefore meant that I could steal his idea for this one. And also Jack Stoddart, who is not here today, but he's a PhD student at the ANU, who helped me by writing our test solver, for example, and various other things. Like I was flying to Portugal while the contest was happening. So while I was on the plane, he was there manning the Discord, so things went smoothly. And of course, thank you to ICFP itself for the sponsorship. The results will be available on our website. And actually, I might see if I can, nope, it's not on the internet. Let me go there because I want to show you. We have, these things are not directly accessible from the website yet, but we have some, oh, it's a bit funny looking, but maybe I can fix this before it goes live. But we have these live rankings throughout the duration of the contest. You can see this highlighted part here is where the lightning round was ending. And then at the end, this is the end of the competition. If we look at one of the winners of the contest, which is Unagi, if I can spot them. Oh, there's another winner of the contest, the Moyo team. You can see that they were sinking down in the rankings during the lightning round, but then very quickly managed to come up with their solution, which kept them towards the top for most of the competition. And so you can see this for all of the teams that participated and scored some points. This will be available online. And so you can see all of those results there. Great. I think that's all I have to say. So thank you very much. And yeah, I'll take any questions if you have any.
Okay, hi. So, my name is Dominique de Vrieze from KU Leuven, Belgium. I was honored to be your PC chair this year. One of the things I get to do is hand out some awards.
Microphone not working well.
Not sure what I'm doing wrong. Yeah. Yeah, I'll just keep it like this, it's fine. So one of the things I get to do is hand out some awards. First, and there will be no surprises here because we saw the 4 nice presentations yesterday. There are some official certificates for the distinguished papers. Before I hand them out, let me just mention...
I can't help with that.
Let me mention the process that we used for selecting these 4 papers. So after all the acceptance decisions had been taken, we nominated, or 10 papers were nominated for Distinguished Paper Awards from the PC, either based on very high review scores or based on an explicit nomination from one of the PC members. Next, we formed a distinguished paper committee, which consisted of, let me see, 1, 2, 3, 4, 5, 6 senior members of the community, all of which were not conflicted with any of the papers. These people worked hard. They read 10 additional papers. And I'm sure we all know how that does take a while to read a research paper properly. They met, I think, 2 times to take the final decision and ended up selecting the 4. The chair was Manuel Serrano, who is sitting there. So thank you, Manuel. With that, let me get to the awards. First award is for our SRC chair, Kimball Germain. Please come to the stage. So Kimball wrote a very nice paper that was presented yesterday on call-guarded abstract definition interpreters. Should I? Congratulations. Second, we have Rufeng Jie, Tom Schrijvers, and Zhengjiang Hu from Peking University and KU Leuven, Belgium. For their paper, Effectful Lenses There and Back with Different Monads. Congratulations. The third distinguished paper is by Anton Lorenzen, Dan Leijen, Wouter Swierstra, and Sam Lindley for their paper First Order Laziness. Congratulations. And finally, last but not least, we have Tsungju Chang and Ningning Ji for their paper Multi-Stage Programming with Splice Variables. Congratulations. The next award I can hand out, or we can award, is the ICFP Most Influential Paper Award for the ICFP paper from 2015 that has been considered by the SIGPLAN Awards Committee as the most influential paper from that year. Maybe should imagine a drum roll now. So the award goes to Andreas Rosberg for his paper 1ML Core and Modules United. Congratulations.
Yeah, thanks for that. I'm flattered. I'm also slightly embarrassed. So I knew a few people quite like that paper. I didn't know it was super influential. I like to think it's like the cherry on top of the previous paper we did, which was the effing modules paper with Claudio Russo and my then postdoc advisor Derek Dreyer, which will never get an award because we sent it to a third grade conference because, in the word of my aforementioned advisor, your advisor was an idiot. So I accept this award gladly, also on behalf of Claudio and Derek as my co-authors. Thank you very much.
And with that, I will pass the microphone to Alex Potanin from the SIGPLAN Executive Committee, I think, who will hand out some other awards.
All right. Is this thing working? Working? Yes, good. Oh, okay. Yes, boss. It was already the right slides. Perfect. Thank you. So yes, I'm Alex. I'm a SIGPLAN treasurer and member of the executive committee, so I'm here on the behalf of the entire SIGPLAN. We have 3 awards today to announce at ICFP. And the way it's going to work, I'm going to announce the award, and then I'm going to invite the person we are awarding to stand embarrassingly on the stage while I read a citation, and then as a reward or punishment, they will have a chance to say a few words. So that's what's going to happen now. So according to the slides, we start with our SIGPLAN John Reynolds Doctoral Dissertation Award. So I would like Harrison Goldstein to please come up and, yes, we can clap, and stay here as I will read the citation. So Harry's dissertation on property-based testing for the people makes groundbreaking contributions to software reliability by advancing the theory and practice of PBT. It introduces novel mathematical foundations, free and reflective generators that automate the construction of high-quality test case generators, dramatically improving usability and effectiveness. And through empirical studies with industrial users, Harry identified the key challenges and addressed them with TAIH? Is that TAIHI? Thank you. An interactive framework that enhances testing visibility and control. The research bridges programming languages, HCI, software engineering, and lays foundation for the new practical, powerful PBT tools with a substantial impact across industry and academia. So let's clap again for Harry. And
I didn't really prepare anything, but I just want to thank my advisor, Benjamin Pierce, all my friends and collaborators who are here and not here. This is just very special for me, and thank you.
Thank you very much. Keep that word. All right, thank you. And the next award, again, SIGPLAN level award. So this is across all conferences and the community that we have, not just ICFP, is the Programming Languages Achievement Award. So maybe a drum roll or something appropriate. And I'd like to invite Martin to come over here. And as before, please stay here while we read the citation. So Martin Adesky has had a profound and lasting impact in the field, as you would probably all have known through his groundbreaking research and transformative practical contributions. With a career spanning so far already over 35 years, he has shaped the design of widely used languages and foundational work in OO type systems and Java generics, and then the creation of Scala, the only academic design language of the 21st century to achieve very widespread mainstream adoption. Scala elegantly combines functional and OO paradigms and has a strong static type system, and the influence is visible across the entire programming ecosystem. Beyond the language itself, Martin's leadership in evolving Scala and founding the Scala Center mentored over 50 successful researchers, probably a lot more than that by now, and continuously bridging research and real-world development that exemplifies the highest standards of the PL community. His work has directly impacted hundreds of thousands of developers worldwide and inspired generations of researchers. And thank you, Martin. Would you like to say a few words?
Thank you very much for this award. I'm very honored to receive it. A project like Scala, of course, builds on many other influential ideas and languages that came before, and is the work of many people. As influences, I just want to mention my advisor, Niklas Wirth. Modular 2 was the first language I liked so much that I wrote a compiler for it, so that's how it all started. I then want to mention Phil Wadler, who with whom I co-designed Pizza. Without Pizza, I don't think I would ever have done Scala, so that was very important. Phil also introduced me to WG 2.8, and I'm thankful for the great interactions and inspirations I got from the people there. I then want to mention all the collaborators, the research students, the postdocs, with whom we did this project. It took many people, lots of work to turn an academic experiment into, in the end, an industrial strength language. And I'm also very delighted to work with my current team, who turned Scala into something that I believe will be even more influential and exciting than what we did so far. Thank you.
All right, and for the final, again, SIGPLAN-wide award in programming languages is an award for a distinguished educator. So final small drum roll. I would like SPJ, Simon Pitton-Jones, to please come over. And that is a long citation that I'm going to read. So Simon's contribution to education are extraordinary. He's arguably done more to advance the cause of computing education in UK schools than any other individual. As a founder of Computing at School initiative and subsequently a chair of the National Centre for Computing Education, Simon led a campaign to recognize CS as a foundational discipline in the national curriculum in the UK. This effort has seen outdated ICT instruction replaced with a modern curriculum focused on algorithms, programming, and computational thinking, equipping students with both theoretical and practical skills. Simon's tireless enthusiasm and ability to unite policymakers, as well as educators and industry, played a central role in the reform, which continues to serve as a model for other countries. And in recognition of these contributions, Simon was made an officer of the Order of the British Empire, OBE, in 2022. Wow. Simon is best known with the SIGPLAN community for his major contributions to the Haskell programming language, a language that has itself played a crucial role in CS education. With clean semantics and powerful type systems, it makes it an ideal language for introducing students to the key concepts in functional programming, such as high-order functions, immutability, and lazy evaluation. In fact, our first course at ANU for years is in Haskell, so we know that. Universities around the world use Haskell as a vehicle for teaching foundational topics and often relying on Simon's textbook, The Implementation of Functional Programming Languages. By providing a practical yet cutting-edge platform, Haskell has helped students and researchers explore advanced ideas while grounding their understanding in real-world applications. Haskell has influenced the design of numerous other languages, ensuring its educational legacy that continues to shape the field. Finally, there's more. Simon is well known as a vibrant speaker. His presentations are characterized by clarity, energy, and accessibility, and as a result, he has long been a sought-after speaker at conferences and frequent contributor to summer schools, mentoring workshops, with advice on how to give talks and write research papers, being invaluable for many students and researchers, which I do point for many years, as it's online on the website. And through his work on curriculum development and programming language innovation, technical communication, and career advice, Simon has made direct and lasting impact on the education of programmers and programming language researchers throughout the world, as well as millions of UK school children. His dedication and achievements make him exceptionally deserving candidate for this SIGPlan Distinguished Educator Award. And would you like to say a few words?
Wait. Yeah. Thank you. I shall be very brief. I've only got one thing to invite you to do, which is to pay attention. So education is complicated, and computing education needs people who know about education and people who know about computer science. So we know not very much about education, I would say myself included, but quite a lot about computer science. But it means we have to get involved. It's no good if we just leave it to schools and policymakers to do this stuff. So get stuck in, folks, and that means not just talk to your governments, but talk to your local school teachers and educators in university. Try to spend a little bit of bandwidth on doing that. It's quite rewarding, actually. Everybody wants young people to have a good education in computing, and it can be a lot of fun helping to do that. So thank you so much for this award. I'm really very proud and pleased. Thank you.
Please.
Yeah.
There we go. Student research competition. There we go.
So my name is Kimball Germain. I'm the chair of the student research competition this year. I do not have any slides. I want to give you a little bit of background on the student research competition first, and then we'll announce the winners. So there are two categories in the research competition, undergraduates and graduates, and we'll be announcing first, second, and third place winners for each category. And in order to get to this point, the participants in the competition had to submit a 3-page abstract, which we had a review committee, and once, if that was accepted, they would then present a poster at the poster session you may have attended last night. And then we, from that poster session at that point, picked 3 finalists in each category. And then they presented lightning talks in the last session just earlier this afternoon. We have a committee that has deliberated after each of these stages to determine who the finalists were and then who the placings were. And so I'm going to go through the undergraduate committee or undergraduate category first, and then the graduate category. And so if you are here, if you would come up to receive your certificate, and while you're coming up, I'll mention a thing or two that the committee thought was noteworthy about your work. So for third place in the undergraduate committee, we have the work on Minimu, which was done by Feng Ding and Kiriel Mortel Abad. The committee, they felt like your presentation was very effective and that this was technically advanced work. In second place in the undergraduate committee, we have Bryson Pinkston for his work, a visualizer for debugging and understanding logic programming through supergranular small-step evaluation semantics. And what the committee liked about this work, they really appreciated the live demo, and they liked that you had grounded something in theory, which seems like it will be very useful. Finally, in first place in the undergraduate category, we have Marvin Borner for his work on optimal effects. The committee was very impressed by his presentation and by the sheer amount of work that he did. On to the graduate category. In third place, we have Ziki Chen for their work towards programming with effect handlers and typed holes. And, sorry. The committee felt like this work was very timely and a very good thing to do for pedagogy, as effect handlers are sometimes difficult for beginners. In second place, we have Brian Se Kai Cheong for his research, an abstract interpretation framework for relating parsing traces in non-deterministic LL and non-deterministic LR. The committee felt that you had very interesting insights and connections and the potential to address some very practical issues in parsing, and appreciated that motivation. Finally, in first place in the graduate category, we have Yongqi Fu for his work, Fixed Point Oriented Programming with Orders. The committee felt like this work was very clearly presented and very well motivated. We, as a committee, want to express our appreciation to all of the students who participated. We found value in all of their contributions. And just as I go, would you please give everybody who participated in the SRC, including the committee, a round of applause? Thank you.
Hello. My name is Eloise. I'm one of the members of the SIGPlan AV team here at ICFP SPLASH this week. We are managing all the AV for this conference, and I'm going to give you a brief report about what we've been doing this week and what we do in general. So we are a volunteer-run organization within SIGPlan, and we consist of students. I'm here, Nicole's at the desk, Alex and Eduardo over here, and Apoorv, Espada, JP, Dexter, and Samar are in the back. We manage the in-room audio, streaming, recording, hybridization, and the archival of all the talks at these SIGPlan conferences. And we cover not just the main tracks, such as ICFP and UPSLA, but also the different workshops that are occurring here throughout this week. Specifically at ICFP SPLASH this week, we are covering up to 8 parallel tracks, including 50 live streams across the entire week. And this week, there's a grand whopping total of about 600 talks across a variety of modalities. Of course, most of these are in person, but we also have about 45 pre-recorded and live remote talks to support those who were not able to present in person this week. We also, in preparation for this conference, exchanged somewhere around 800 emails, so this was one of our bigger conferences, our biggest yet, in fact. We want to give many thanks to a lot of the people who were able to help us manage the AV for this conference. So in particular, we'd like to really thank the general chairs, Ilya and Charles. It has been really excellent to work with you, helping us navigate Singapore, figure out the AV equipment rentals, the AV purchases, working with the different vendors, and most importantly, we really want to thank you for trusting us to help you this week. We'd also like to give a shout out to the local chair, Waihan, who has also been hugely helpful with working with the different vendors. The general chairs and the local chair have been super communicative, always keeping us in the loop with everything that we needed, and we really appreciate that. We'd also like to thank the organizing chairs of all the different events, particularly for helping us to get into contact with all of the presenters this week, so that way we could prepare for everyone's talks and all the different ways that they're being presented. We also thank the SV chairs, Luis, Yonzhang, Michelle, and Joe, who provide us with a team of student volunteers who are assisting us this week. It would not be possible for us to be able to do the work that we're doing in the way that we are without the team of video volunteers to manage the talks. And finally, some special thanks to the teams at Conference Publishing and Researcher who, upon our request, have been updating their systems to provide us with some information that helps us prepare for these conferences more efficiently. And I'll talk a little bit about our process, so how we manage the different conferences. So generally speaking, we start with some long-term preparation by coordinating with the GC and the local chair. In particular, a lot of our work here is assisting with reviewing the AV rental contracts to ensure that the equipment is being rented or purchased economically while still providing valuable equipment so that we can provide a good service for streaming and recording and managing these talks here. Closer to the conference, we also send out an AV presenter questionnaire. A lot of you may have received this, and I really want to thank you for filling this out. This helps us prepare for the talks and all the different modalities that they might be given. As part of this, we also collect streaming and recording releases. This is an important legal requirement in order for the ACM to be able to host your talks online. And so completing these is important, and we thank you for completing those. We also work on ensuring that the equipment and the workflows are ready for the conference, and we're constantly iterating on them so that way the process can be even easier for those who are presenting their talks. We arrive on site a few days before the conference in order to set up equipment in all the rooms. Then we train the video volunteers so that way they can manage the talks each day. Then we set up the live streams and the recording, and then throughout the week we're just keeping tabs on all of the talks to make sure that they're running as smoothly as possible. And finally, after the conference has wrapped up, we review and edit all of the recordings, and we upload them to YouTube as well as the ACM digital library for archival. Here's some pictures of us working throughout the week. First, we have us setting up at the National University of Singapore, and then you can see all of our equipment as well as the student volunteer team who's been helping us. Looking ahead, of course, the next SIGPLAN conference is going to be POPL in January. Planning is well underway, and we've been working with the general chair, Sandrine. We're expecting up to 6 parallel tracks, as well as 15 total tracks across the entire week. We're also in contact with the SIGPLAN Executive Committee Treasurer, Alex Potanin, to integrate ourselves more closely with the SIGPLAN organization, in particular looking into making AV a budgeted function of SIGPLAN, and so that this could reduce conference expenditures by taking more equipment in-house so it doesn't need to be rented for every individual conference. And for future general chairs, we want to note that we can help figure out AV logistics at the different conferences. Every conference is different, but we have a lot of cross-conference knowledge that we can share to help the AV portion run as smoothly as possible. And we want to note that AV vendors might be more expensive than necessary, particularly because we have a large amount of equipment already in-house that we can reuse at each conference, and so it doesn't need to be newly rented each time. So if you're looking to work with us, it's great if you can contact us early and keep us in the loop, and our email is on the slide here. And finally, you can come find us at any time this week. We're here the entire week. Come chat with us. We're always looking for more volunteers to join our team as well. So if you'd be interested in working with SIGPlan AV, let us know. You can find us online on the SIGPlan website, on our email, as well as our YouTube channel, which we're very proud to say recently reached above 10,000 subscribers. Thank you.
Test. Ah, yeah. Okay, so I'm less proficient with AV machinery than Eloise, so I'm going to stick to this microphone. Traditionally, as PC chair, I'm also expected to give a bit of a insight into the process of how we composed the ICFP program. Of course, that's work that I haven't done alone, so there's a bunch of people to thank. I'm gonna show you a long list of names. People who are in the room, you're welcome to stand up and wave to the audience. We can maybe combine the applauses for the different things towards the end. So first, two people that did a lot of work are the associate PC chairs. So there's Peter Thiemann from Freiburg University and Manuel Serrano from Indria in France. Manuel is also the PC chair for next year. So if you're here, please stand up. Next, there was a very expert program committee with 60 members, in addition to the three of us. Those of you who are here, please stand up. We had a bunch of external reviewers, I think about 50. I don't know if those people are also happen to be here. If you are here, please stand up. And finally, several PC members involved some of their students in the reviewing. I think this is personally, I think this is quite a good practice to give, let's say, talented and a bit senior students a bit of insight in how the reviewing process works on the inside. So if any of the people here are in the room, please stand up. Okay, with that out of the way, some statistics about ICFP this year. We had 110 submitted papers, and we ended up accepting 36, which means we had an acceptance rate of about 1/3. This is on par with previous years. This is both the total amount and the acceptance rate is similar than previous years. So I think ICFP is doing quite well. We worked with a 2-round process. That means in the first round, all papers were conditionally accepted. They got, let's say, required changes, required improvements that they had to make. For some papers, this was relatively limited. It was just fixing the sometimes minor remarks of reviewers. For some papers, this was more strict. There were like mandatory changes and in several cases, or in many cases, I think we were, as the PC was essentially unsure whether all these papers would end up being accepted. So this was not just a pro forma thing. This was a real mandatory changes that we expected. However, it seems all the authors did their homework very, very well, and we ended up satisfied with the changes in all these cases. Additionally, Derek already mentioned on Monday that there's a sort of standing agreement with the Journal of Functional Programming for what's called Journal First papers. This year, 9 JFP papers elected to present their work also at ICFP. I'm sure many of you saw these presentations already. They are intermixed with the rest of the program. Some further statistics. I tried to gather some statistics from the submission system about where we get submissions. I think it's not new that there's a bit of an imbalance between, let's say, all the continents of the world. So functional programming still appears to be mainly researched in Europe and North America and a bit in Asia. Other continents are largely missing. There's a few Australian papers in the top there, and I think there's a few from South America as well, but not many. I don't know if we as a community can do something about that, but this is the state of it. By the way, what I'm showing are numbers for author-paper pairs. So if one author submitted multiple papers, he will be counted multiple times. So just to be correct. The acceptance rates were a bit different among let's say, the origins of the vocations. I found this interesting. I don't know if I have a good explanation. Of course, for individual countries, there are sometimes only a few submissions. So sometimes we have wide discrepancies. At the level of continents, also there's sometimes significant differences. I'm showing you some statistics. I'm not sure what exactly we learned from this, but it might be interesting. This is a slide that Ilya suggested I remove because it didn't contain any useful information, but I disagree. So one of the things that we as PC chairs and as associate PC chairs, when we assign reviewers and when we invite external reviewers, I think this slide shows what we strive for. So at ICFP, what we strive for is high quality reviewing. Particularly, we aim for 2 expert reviews per submitted paper. As you can see, I'm not sure if this is clear. So this is on the left, we see the amount of expert reviewers, and here the amount of, the amount of knowledgeable reviewers, which is the second highest expertise level. So you can see that in total, one paper had 4 expert reviewers, 11 had 3 expert reviewers, 44 had 2 expert reviewers. So this is where we reached our ambition. 40 papers had 1 expert reviewer, and 3 had no expert reviewer. So this is sort of what we try to avoid. I can tell you that this is not easy to always make sure there's an expert. So for some papers, they're in a very niche topic, and then you invite an external reviewer who tells you that he thinks he's going to be able to provide an expert review, and then 3 days before the deadline, they submit a knowledgeable review. So this happens. It's not easy. However, I'm actually quite satisfied with these numbers. So I think in the large majority of cases, I think we did very high quality reviewing, and I think as a program committee, and definitely I as a program chair, I'm proud of these numbers, so that's why I wanted to show them. There's a few, I think on the whole, I'm personally satisfied with how the reviewing process went. I hope the authors agreed. Maybe the ones in the room are the ones that have presented, so they may be more satisfied than the average submitters. But I hope also the people who submitted papers that got rejected are also happy with the feedback that they got. I listed a few lessons learned here, or things that I think as a community might be worth thinking about. I don't think they're major things. One thing that I think we should look at is institutional conflicts at very large organizations. For example, INRIA is a French research organization with, I think, about 2,500 researchers in total. if all of, so what happens is when you're in a PC, you have to fill in a list of names or a list of institutions that you are conflicted with. People who work for INRIA or for these other large organizations, they all have a bit of their own policy of what they should do with this. Some people mark all of INRIA as conflicted. Some people mark sort of the sub-organization of INRIA that they work for or the location as conflicted. I think it would be useful to have a bit more policy there. And I think considering 2,500 people, almost the large majority of people who work on programming languages in a country as conflicted is not a good practice. So I think we should be a bit more narrow there. I think a policy is needed, but maybe this needs to be taken up at SIGPLAN level. And second, one thing I would have done differently in hindsight is the reviewing model for second round reviewing. So what we did this year, it was essentially what I call a single shot resubmission model. That meant reviewers got mandatory revision criteria, and then essentially they had one shot to resubmit. We had not designated a shepherd. That meant that there was, and I didn't realize this up front, but that meant that there wasn't really a way for authors to ask clarifications about these revision criteria, or not in an efficient way at least. I think we ended up pragmatically resolving the situation. We allowed some communication in a few cases, and I think we treated all authors fairly. However, I think personally I would recommend to move to a bit more of a shepherding model, where after round one we designate one of the reviewers as a kind of shepherd who can then communicate with the authors, provide clarifications if necessary, etc. So, but of course, this is something that will have to be taken up by my successor, Manuel Serrano, who will, I'm sure, have his own opinion about that and decide what to do. Before I forget, I think Ilya will, in his general chair report, still provide a few thank yous to many people. However, I think it's important that we don't forget someone who has done a lot of work on this conference. I took the liberty of providing a thank you present for Ilya. So, as Simon said, we don't necessarily know much about teaching, but one of the things I learned about teaching is that, sorry, let's take a picture.
Thank you.
So when Ilya was doing his PhD in Belgium, we sometimes had events together. One of the things I taught Ilya at the time was that you should drink good beer from a glass that is adapted to the kind of beer you're drinking. One of the things I learned about teaching is repetition is the mother of teaching.
Thank you so much.
Yes.
Thank you for the lesson.
I hope you enjoy. So thanks, Ilya, for the large amount of work that you did on making ICFP successful. And with that, this is all I wanted to say. So thank you, and I'm passing the microphone to Ilya now.
Thank you, Dominic. Wow, I'm so gonna enjoy it. Yeah, good. So this is almost the last thing. I'll try to keep it short, but this is also very important, so prepare to do some clapping. Let's have the slides. Yeah, okay, awesome. So this year, as you very well known, we have a very unusual ICFP. So it goes in overlap with many SPLASH UPSLA events. And when ICFP, well, the main ICFP conference ends on Wednesday, next day we have the big UPSLA event starting, and ICFP events such as Haskell, Symposium, OCaml, and Schema, and Miniconvern continue. So since I was also kind of informally appointed as the local chair for the whole joint ICFP SPLASH event. For me, on some occasions was difficult to distinguish where ICFP ends where SPLASH starts. So, well, when they told me it's going to be a lot of work, obviously that was clear. What was not apparent to me is how important it for many people to work together in tandem and also be very, very kind to each other. So this presentation is essentially a thank you to all these many people who made this big event possible. Okay, so just very quickly, there are some numbers. I would love to say that this is the largest SIGPLAN event in history, but that wouldn't be true because in early 2000, Uppsala was very, very big. But I think in the last couple of decades, this is certainly one of the larger ones. So today we have close to 600 people on site. So this is as of a couple of days ago. We had a few more registrations, and the largest day is going to be Thursday, when we will have both Haskell Symposium and Uppsala starting. Okay, I'm very pleased that close to half of the attendees are students. So it's very nice for them, like for such a large fraction of population being the junior researchers. Okay, so this is a distribution of geography. I don't know what lessons we can take from here, except that if you organize a conference in a country, that country ends up being in the top 3 amongst the attendees. Okay, so this is the distribution by the continent, which I think is quite consistent with what we have expected. So as a very large event, we wouldn't be able to do so well in terms of registration costs and amenities without our wonderful sponsors. So that the first thing goes to the big 4 sponsors who gave us a lot of funding: Huawei, Ahrefs, Standard Chartered, and Amazon AWS. So let's give them a round of applause. One thing that it was remarkable is that there were several companies that were so eager to sponsor both ICFP and SPLASH that we had to come up with special categories and special ranges of benefits to make them all equally distinguished contributors. And then we had the several organizations that also very heavily contributed to this whole event. So this is my home institution, National University of Singapore, Singapore Tourism Board, which here for some reason gave me a logo that says Singapore Exhibition and Convention Bureau, and also MGD Pro Group, which very generously provided pro bono lots of the AV equipment for the conference. So a round of applause, please. And finally, all other wonderful sponsors. So many of them have their tables outside in the corridor. Please take a chance to talk to them and see if they are hiring, because I believe they do. So thank you. Okay, and now going on to people. As I said, every single person involved in the organization went well beyond the call of duty, and that's why I think it's really important to acknowledge this work. So this conference would not be possible without the amazing event and logistic team of National University of Singapore. Philip is here in the room, and other people are busy now at the registration desk. So if you walk by, take a chance to say thanks to them, because they actually did most of the work to make this event like logistically possible. So let's give them a round of applause, please. So a lot of organization has been done with my partner in crime, Charles Zhang, professor at Hong Kong University of Science Technology. So he is a general chair for SPLASH. I'm actually not sure if he is on site, and he might be actually arriving this evening. So, but let's give them a round of applause anyways. And of course, our wonderful ICFP program committee chair, Dominique De Vries, so who shouldn't go unthanked. Right here. Uppsala is about to start in 2 days, so in advance, let's give a big round of applause to the reviewing committee chairs of Uppsala, Sukyong Roo and Shriram Krishnamurthy. Okay, so this is actually quite important. So as many people who come to SIGPLAN conferences, and I don't know if this is the case for others, but I certainly took the presence of absolutely amazing AV support pretty much for granted. So we have this really nice setups between the talks, and we have the YouTube channel that works flawlessly, and we have Discord, which functions without any problems. And I just didn't realize how much work goes into that. And so we have 9 AV chairs: Alex, Apoorv, Guillermo, Nicole, Eduardo, Angel, Jean-Paul, Eloise, and some are here on site. And these people did more than a ton of work, and they are just amazing. So give them a huge round of applause, please. Yeah. They are truly one of the treasures that SIGPLAN community has. So let's cherish them, please. Okay, so another big round of thanks goes to our tirelessly working student volunteer chairs, Louis, Yung-Jong, Michelle, and Joe Watso, who are running the show here with all the student volunteers. So a round of applause then. Yep. So these are all the student volunteers. I apologize, I'm not going to read all the names, but if you see them, thank them. You can see them in these red T-shirts. And I'm very pleased that we have nearly 70 of them at this conference, and it's also great that we were able to support that many student volunteers this year. But please, let's thank them for their hard work. Wonderful. So we have 30 collocated events. Most of them are workshops. And this is where huge thanks go to the 4 workshop chairs that we have for the combined event: Ben Greenman, Chandra Nandi, Sasha Misailovic, and Jeff Huang. So a round of applause to them, please. Sponsorship. So lots of liaison with the sponsor has been done by 2 amazing sponsorship chairs. Dan Vinogradkort, who is also at the NEC3 booth, feeling a little bit lonely at times, as he said, because he is there in the far corner. So if you have a chance to come and say hi to him, please do. And also Martin Kellogg, who was responsible for the splash part. Okay, so we had weapon publicity. Many of you are on Twitter and Blue Sky. So if you see these funny tweets coming up and the website is working, that's thanks to Umar, Jule, and Sam, who are in charge of weapon publicity. Okay, PLMW took place on Sunday. I've been told it was a huge success, and for that we have to thank Lucas, Miljana, Ninning, and Conrad. Doctoral Symposium Chair Conrad Watt. A round of applause to him, please. I told you that's many people, so that's takes a big crowd to run this conference. Student Research Competition Chair. So we have Kimball here, and we have Yulei and Subhajit handling the SRC for Splash. A round of applause to them as well. Okay, so we have a number of DEI events. So we had one lunch today, another tomorrow, and the Women in PL dinner tomorrow night. So lots of logistics for that has been handled by Michael, Alejandro, and Casey. So please, a round of applause to them as well. Okay, big one goes to Liam for running that fabulous contest. I have to say, I was immensely happy that I managed to recruit Liam. I didn't disclose to him how much work is it to run the contest, but I knew. I ran one 6 years ago, and I think it was absolutely amazing. So yeah, thank you, Liam. Okay, so ICFP had artifact evaluation this year. I'm not sure if Benoit or Leonel are in the audience, but I saw Leonel here, so please, let's give them a round of applause. Okay, so yes, so I'm skipping Chirun because I know he's not here and he's going to get another round on Thursday. I've been told that at least 30 or 40 people showed up for the Saturday hike. And it was fun. Yes, I didn't like that. So sadly, Manuel, who planned and charted and actually has another hike for Sunday, had to urgently, for the family reason, fly back to Austria, but he's going to be back for the rest of the conference. So he's our newly appointed outdoor activity chair. So let's give him a round of applause. Very, very delighted to have him as a colleague. Okay, as always, Niringa, so our tireless SIGPLAN conference manager. Please, let's applaud her. Okay, I personally want to thank the 3 people who provided a lot of advice from how to run Splash and ICFP and how it has been done in the past. So Nick, Marco, and Manu. I think none of them are here physically, but let's give them a round of applause as well. Well, okay, it's about to get good. So several people asked me how it happened that we have 2 conferences together. So I actually have to thank a particular person for that. So the guy who convinced me that running ICFP and Splash together would be a good idea, Jan Vitek. Let's thank him for that. And finally, so the reason why you didn't see too much venting from me on social media or in response emails, for that, the huge thanks goes to the mental support chair, Alex Potanin, who actually had to listen to all of that. Let's thank him here. Okay, so thanks a lot to all the organizers of co-located events, authors who submitted the papers, and also all the attendees who showed up, and hopefully all of you will have fun for the remaining 4 days of the conference. So please enjoy. Thank you so much.
Sam Tobin Hoogstad is the General Chair for ICFP 2026, and we will now have the official announcement of where it will take place. So he's unfortunately not here physically, so we hope.
Hello everyone. I hope you can all hear me, and I'm very excited to be able to announce ICFP 2026. So, without further ado, ICFP 2026 will be held in Indianapolis in the United States. Indianapolis is a beautiful city where we have museums, the State House, an exciting downtown, the Canal District, monuments, and historic neighborhoods, hip places to visit, and more. The conference will be held on the campus of the brand new IU Indianapolis, which is the home of part of the Luddy School for Informatics, Computing, and Engineering. And the Luddy School has a special contribution to the history of functional programming. I particularly am fond of the following paper written at the Luddy School almost 50 years ago. 50 years ago when we will be having this conference in Indianapolis. Cons should not evaluate its arguments. One of the first papers to develop non-strict functional programming. Indianapolis is easy to get to. It boasts the #1 rated airport in the entire United States, with flights to Europe as well as all over the country. The campus of IU Indianapolis is a mere 15-minute walk to museums, to the state capitol, and close to numerous other attractions in Indianapolis. The conference will take place in Hine Hall on the campus with generous sponsorship by the IU Luddy School to arrange this. Hine Hall is a beautiful and modern facility which has great opportunities for receptions, talks, meetings, and hanging out with the ICFP community. The workshops will take place additionally in University Tower adjacent to Hine Hall, another excellent conference facility. We will not be located in a hotel, but there are numerous hotels, easy walking distance listed here. Indianapolis is one of the primary convention destinations in the United States and has numerous lodging facilities for anyone and anywhere and any desires that you have. The organizing committee for ICFP 2026 includes Manuel Serrano, who was just mentioned for the hard work that he's already been putting in, Robbie Findler, the associate program chair, Sam, the publicity chair, Jules Jacobs, the web chair, Daniel Winograd Court, industrial relations chair, many more people who have already begun working on this, and potentially you as a volunteer, a contributor, or an author for ICFP 2026. The submission deadline for ICFP 2026 will be February 19th, with notifications on May 14th and final decisions on June 10th. ICFP will take place at the end of August in 2026, with the primary conference August 25th through 27th, and the workshops before and after. We're incredibly excited to welcome all of you to Indiana and to Indiana University for ICFP 2026. Start your engines. Thank you.